Okay. Okay. All right. The question was, what did we do last week, kinda? So let me go through on Blackboard sort of swiftly here and show you where to find things. So I shouldn't have done that, but I think I can still get there from here. Okay. Now, where I'm going to go is content. I think that's no. Okay, course content. Let's start there. Okay, now I'm going to have to move y'all around a little bit because it's just Zoom puts blocks there so I can see who's some of the people who are here, but then Blackboard, those blocks cover some of what I'm trying to do. So y'all can see my content for this course, right? Now, what I'm going to do is scroll down here to weekly assignments and activities. I'm going to open that. Usually use the down arrow key for that. So let's open it. And then it's going to open the various weeks. So let's go to week 1. Okay. Now, the overview and weekly to-do list, that's just blah, 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 blah. The instruction materials, that's where most of the stuff is located. So I'm going to open instruction materials for week 1. Okay, there are the PowerPoints for chapters 1 and 2. We mostly did chapter 1 in week 1. Here is the YouTube video playlist that you can go to and hear everything that went on in every class since the beginning of the term, plus some of the stuff that went on in previous classes, like last spring when I taught this course. So everything is out there on the playlist. The stuff at the bottom of the playlist are the things recorded this term. The stuff at the top of the playlist was the stuff that was recorded last spring or earlier. Okay. Here are the handouts. This was the research paper instruction. Here is the locator card. And here are the labs. This is where you click to get to this lab simulations. All we're doing are simulated labs now. You click on this one for the simulation. Here is the lab sheet that you fill out based on that simulation. Now, you can either do it according to the instructions that are on this sheet, or if you print out the sheet and then go to the recorded lectures where we had lab 1, you can go through that. Okay. Now, and then this is a library services for physical science. It's just something they sent me from the library, so I posted it here. Okay. So that's your first lab that we did in week 1. This is the place you go to access that. It's a lab simulation. Now, I can't guarantee that all of you will be able to open the simulation, but even if you can't, you can go to the YouTube videos and see that. Okay, so that's week 1, lab 1 that you were asking about, right? Now, I want to show you something else here. All right, I'm going to close this out. Okay, here is lab 1. That was under instruction materials. Now, I want to show you what's happening here. When it says lab 1 here, if they had put a plus sign here, I would have put the lab here as well. They did not, so I can't put the lab here. However, a few people maybe, yes, 2 people have already submitted the labs through here. You don't have to, but you could. So that's why you see lab 1 here. The lab itself isn't there, but you can submit the lab there if you choose. It's not a requirement. Okay, I'm going to move y'all out of the way again. I'm having to go back and forth. Okay, so they put all this mess on Blackboard, and it just, to me, makes it more confusing for the students to figure out what to do where. Okay, now what I'm going to do now is move y'all again. It's so awkward. Okay, there was lab 1, and here's test 1. Okay, now I'm going to click on test 1. This was the first week, week 1 again. And again, they did not put a plus sign here. So I couldn't put test 1 here, but already a couple of students have submitted their test here under test 1. You don't have to, but you certainly can if you want to. Okay, now, all right, I'll move y'all again. Okay, now I'm going to go back to the top. And the reason I'm going to the top is, do you see these icons up here? This one that looks like an envelope, and when you put your cursor on it, it says messages. Okay, I'm going to click on the messages. You click on that, you'll see several people have submitted work through messages. That's perfectly fine. Perfectly fine. Now, I'm going to have to move y'all again. This is so awkward. Okay. Here is where I put the second test that I'll talk to you a little bit later, but since we're here, I wanted to show it to you. And here also is where I put the first test. Attached, I don't know why that is like, okay, it's test 1. So I could not post it under week 1, so I put it here. So the test 1 tab, blah, blah, blah. Okay. So that's where you find the first test, which I think is what you're looking for. That's also found where you find the second test, which is right here, which we'll talk about later today. Okay, so there was week 1. Lab 1 is under instructional materials. Test 1 is under messages. Okay, so now let's go to yuck. It kicked me out of, that's what the yuck was about. Okay, let's go to week 2. That's the one we finished last week. So again, click on the arrow here and then scroll down until you find week 2 here. Okay, I'm going to open week 2. There's the overview and to-do list. Here's the instruction materials. Okay, I'm going to click on that again. All right, there was chapter 2 PowerPoints. We didn't get into chapter 3, so all we had was that one. There's the YouTube video where it references it. You go back to week 1 and access it. Okay, the handouts, it says see the research paper instructions and locator card links given in week 1. Here are the 2 labs. There's that link again. Now I didn't do it as a web link here. What you would have to do here, either go to week 1 or week 3 and just click on it, or copy this and put it in the command line up here and open it that way. Either one of those 2 ways. Here is the sheet that we filled out for lab 2, and here's the sheet we filled out for lab 3. This we did on Tuesday, this we did on Thursday of last week. Okay, so that was week 2. All right, so that's where you find the labs there, and the site is right here, but you can't click on this. You have to copy this to the command line. Okay, now let's close that one out. And here it says lab 2 again, but again, if you click on lab 2, and this is what makes this Blackboard so awkward, there's so many places you can go. Again, they didn't put the plus sign, so I couldn't put the lab here either. But already 2 people have submitted things. You can submit there, or you can submit through messages like you saw other people doing. Or you can send me an email. That's perfectly fine too. Attach it to an email. All right. Let me get out of lab 2, and now we're going down to week 3, which is this week right now. Okay, so here's week 3. Again, instructional materials, click on that, and you'll find the chapter 2 PowerPoints. We're going to finish those today. We'll start chapter 3 today, I hope, if I ever quit talking. Go back to week 1 to see your YouTube video playlist. That's where you can click on that. Your handouts are in week 1 also. Research paper instruction locator cards. Here at this time I did put the link here. All you have to do is click on this and that will open up. Here's the lab 4, which we're going to do today. Here's lab 5, which we're going to do on Thursday. Okay, so the labs are typically in the instructional materials. The test will typically be under Blackboard messages. Okay, you can submit the labs either in an email, Blackboard messages, or the lab or test icon that you see there. Now, is this somebody else trying to come in? Let me see. Yes, Rucker is here. So let me get Rucker here. If I can find my pen. Rucker is here. All right. Now, did that answer at least most of your questions? Anybody? All right. Say that again. Okay, you're coming across very broken up. Is this Tobias talking? Okay. I'm not able to understand you because I think the internet is very, very unstable. Mine seems to be good, but earlier today I lost all internet access completely. Now it's back. On all 3 of my morning classes, there were internet problems. So I don't know why, there just seems to be. So whoever was just speaking, try it one more time. Okay, it started real well and then it faded out. Okay.
Just type it into chat. I'll read it to him.
Okay, thank you. All right, while y'all are getting that straightened out, let me go back to getting the class set up for today. I can hear you. It's a little bit better. What you got? I can't hear anything now. I take it this is Tobias talking. I cannot hear you. Okay. Angelita, has he sent a chat yet?
No, sir.
Okay. All right. I'm sorry. It's just the system. I think the whole infrastructure is really, really weak. And I have 5 bars on my internet here, but I had 5 bars earlier with no access. So I don't know. It makes no sense. But anyway, that's the deal. Okay. As soon as you can get back in, let me know. I guess it was Tobias. Okay, here is somebody else is entering the waiting room and it's a phone number. So you'll have to let me know what the phone number, who this is. Valerie. Okay, welcome. Okay, Valerie's here. Okay, let me do my new share here. I had it up, but then I lost it. And we will go from current slide. Okay, and let's see. Let me make sure there's nobody else waiting. Okay, I should have 9 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've actually lost somebody that was here before. I don't know who it is now. I'm wondering if it's Tobias because he had such a poor connection. But we'll just have to move in. So as soon as I see someone coming back in, I'll let you back. All right. Any questions?
How are you feeling today?
Actually feeling okay. My treatment, thanks for asking, but the treatments last week went incredibly well. Okay. I Thursday had the 10% treatment, and I swear I could just feel the battle going on inside. Is that monoclonal antibody was just attacking those white cells. I was hot. I had to keep eating ice just to to be able to not feel like I was going to throw up or something, but it was very, very effective. Then on Friday when I had the 90% treatment, boy, it was a piece of cake. I felt a little warm and stuff like this. I could tell there was still some battling going on in there, but it wasn't nearly as bad as, oh, here's Tobias coming back in. Let me see. Let me make sure I still have him here. Yes. So Tobias, can you hear or speak any better now than you could before? Okay. I can hear, it sounds like wind or something in the background. Okay. So Tobias, try to say something now.
I was asking you submit the lab test.
Okay, something about submitting the lab. Wait just a minute. Let me let Diana in. Diana is here. Okay, now you're saying something about the lab or the test. I didn't quite understand.
So what do you submit the test again?
Okay. I take it you were asking how you submit the test or when? How?
Yeah, like
Yeah. Okay. When you do the,
like do we submit the lab?
okay. All right. Lab or test, either one. Okay. You have three options. Yeah, three options. One thing, if you've got it and you want to send it as an attachment to an email, email it to me. Perfectly fine. Another option, if you want to attach it to a message, that Blackboard message, the little envelope there at the top of the page on Blackboard, you can send it that way. Okay? Or that under the weekly activities, you'll see under week 1, you'll see a lab 1 and I believe a test 1. Okay? If you want to, you can attach it that way as well. Under week 2, you'll see a lab 2, but no test 2, just lab 2. You can send it that way. I don't have a way for you to send lab 3 under the weekly activities. Okay? So the lab 3 you'll need to send through Blackboard message or email. Either one. Attach it to either one. They only allow a certain number of things for me to allow you to send them directly. So when you see it there, you can send it that way. If you don't see it there, send it through Blackboard message or email. Now, someone was asking how I was doing. For those who may not know, I had I want to say chemo. It was sort of chemo. What it is a monoclonal antibody. It's not a really harsh chemotherapy, but I have a form of leukemia, and I had to have a treatment last week, both Thursday and Friday, and they went incredibly well. But on the other hand, I was very anemic before I had the treatment because the white cells were crowding out the red cells. But then after the treatment, I'm even more anemic because the monoclonal antibody doesn't just attack the white cells, it attacks some red cells as well. So I am tired. I haven't been sleeping well because, I don't know, this is messing with my heart rate and other things this time more than I've had before. But it seems to be getting better now. It also sort of messed with my stomach. Today has not been a very good day that way, but it seems to be better now. So thanks for asking, probably more detail than you really wanted to know, but I am doing much better than I was. Still tired, still low blood, hemoglobin and low energy level, but I feel better than I did, say, a couple days ago. Okay, so hopefully I'll make it through okay today with no sweat. All right, any other questions before we get going on today's class? All right, now where we left off last time, we're in chapter 2. The title of chapter 2 is Motion. We're in section 2.7, which is momentum. Now momentum is an interesting quantity, okay? And I'm going to see if I can do a little writing on the screen here. If you recall, we've talked about several quantities of physics, you might say. Okay, first we talked about displacement. Okay, I can't get my pen to write. That's the vector quantity. Or the magnitude of displacement is just distance. That's a scalar quantity. Vectors have direction. Scalars just have magnitude. Okay? Then when you take the time rate of change of displacement, you get a velocity, which is a vector quantity, or you get the speed, which sometimes they just do little v without the arrow over it. The arrow indicates it's a vector. That is the speed, little v. Time rate of change of velocity, you get acceleration. Acceleration is a vector quantity. Okay? And then you can talk about the magnitude of the acceleration, just little a, without the arrow over it. Now, we also talked about forces. Forces are vector quantities, okay? And what a force is a mass times an acceleration, okay? That's why it's a vector quantity, because acceleration is a vector quantity, okay? Distance or displacement, those are just measured in distance units. Meters, feet, inches, millimeters, centimeters, miles, kilometers, whatever. Those are distances. Velocities, because it's a time rate of change, this would be, I'm just going to write the SI units, this would be meter per second. This would just be meters. Acceleration, since it's the time rate of change of velocity, that would be meter per second squared. You divide by a second time. Okay? Forces, however, are mass times acceleration. So this would be, mass is measured in kilograms in the SI units times meter per second squared. Okay? Vector quantity. Okay? And you can talk about the magnitude of a force, and quite often the book does, and not put the vector symbol over the top. Okay. Why did I go through all that? Just to indicate to you there are other measures of motion as well. And one of these is momentum. Momentum is also a vector quantity because it's a mass times a velocity. Notice the force is a mass times acceleration. This is a mass times velocity. Its units are kilogram, meter per second, because meters per second. Acceleration is meter per second squared. That's because you have a second squared here. Now, let me also say this. A kilogram meter per second squared is called a Newton. They gave it that name after Sir Isaac Newton. Here is the kind of the weird part of this, and I think I'm right on this. I don't read Latin, and Newton wrote his Principia, which is his big work, in Latin, so I don't even know what it is. But my understanding is when Newton was talking about motion, he was talking about momentum. He called it the quantity of motion, which was the product of the mass times the times velocity. He didn't talk that much, he did some about forces, but he was talking more about the quantity of motion, okay, which is momentum. This was his thing. Yet they named the unit for force after him, not the unit for momentum. I always thought that was not quite fair. I think he would have appreciated having momentum named after him, not that. But there is no special name for momentum. It's just kilogram meter per second. Okay? Mass times velocity. Okay. Now, it's an important property closely related to Newton's second law. Basically, if you remember, this is the fundamental equation of Newton's second law. And you see how similar it is. Force is a vector, momentum is a vector. Mass, here it's velocity, there's acceleration. Both of those are vector quantities. Very closely related to Newton's second law. It includes the effect both of the motion, that's your velocity component, and the inertia, that's the mass component. Okay? So there's what we have for momentum. Okay? The units are simply kilogram meter per second. There is a shorthand like Newton or something else. Actually, we will run into one other unit. You can call it, but it's not a single name. It's a compound name, but just not that compounded. All right, any questions about what momentum is? All right. Let me remove some of my scratch here so you can see the slide a little bit better. Here we have the astronaut out there in space, and here we have the spacecraft, and he's going to push against this. The mass of the astronaut was 60 kilograms. Okay. His velocity, or his or her velocity, is 0.75 meters per second in the opposite direction. Remember, velocity is a vector quantity. You have to specify what direction. To the left. The mass of the spacecraft here is 120 kilograms, twice as massive as the astronaut is, but its velocity is 0.375 meters per second to the right. Okay, now here's the assumption here. They really don't go into this in great detail in the book. They probably explain it a little bit better. If initially the astronaut was hanging around there near the spacecraft is twice as massive as the astronaut, and the astronaut pushed on the spacecraft, then the spacecraft pushes on the astronaut, and the astronaut goes this way, the spacecraft goes this way. The astronaut goes twice as fast as the spacecraft because the spacecraft is twice as massive as the astronaut is. Okay? Now, the deal here, before the astronaut pushed on the spacecraft, the momentum of the system, the entire system, was zero because it was the mass times no velocity. They were just hanging there. But as soon as he pushed, now he has momentum in this direction, the spacecraft has in that direction. If you multiply these together, here's Leon coming in, which is good to see. Let me get Leon marked here. If I can find my roll sheet again. Leon is here. Good. Whoops. I think what I did last time, I put who was it? Was it when I said I marked you here, but I didn't see where I marked you? I think it was Brianna. Oh, no problem. This is Leon talking? Okay, yeah. I just marked you here, so I saw you when you were coming in. Okay. And we're on in Chapter 2, Motion, Section 2.7, Momentum, and we're on page 47, and this figure right here is on the bottom right-hand column of 47. Okay. Before the astronaut pushed, neither the astronaut nor the spacecraft had any velocity. So therefore the momentum was zero. However, when the astronaut pushed on the spacecraft, it pushed the astronaut this way, the spacecraft this way. Mass of the astronaut was 60 times the velocity of the astronaut, 0.75. So 3/4 of 60 would be 45 kilogram meter per second. Notice that's the unit we have for momentum. But that's to the left. Okay. The spacecraft, though, moved to the right. It had a mass of 120, and this was 3/8. And if you, I don't do that one in my head as easily, but if you've got a calculator, pull it out here. I've got my phone. Okay. And do 120 times 0.375. And you get 45 kilograms meters per second again. Well, but that's to the right. Okay, astronaut moved to the left, spacecraft to the right. You add those together, vector quantities adding, equal magnitude, opposite directions, it still adds to zero. So if they had put these in correctly, they would have probably put this as a negative, that as a positive. You add them together, you still get zero. That's the special thing about momentum that's not true of forces. Momentum is usually conserved. Forces are not conserved. What do we mean by conserved? That when you add up what it was before you did something, add up what happens afterwards, it has to come out the same. Okay? Forces are not that way, momentum is. And I think that's probably why Newton used that as his quantity of motion, okay? Momentum, the product of the mass times the acceleration. Mass relating to inertia, velocity relating to the motion. All right, any questions on that? Now, that then leads, if I could get the slide to progress here, to a concept that we call conservation of momentum, which is exactly what I was just talking about, okay? I just didn't use that term for it because, as I said, momentum is conserved. The same momentum the system had before the interaction, same momentum it's going to have afterwards, okay? And here's probably not the best example, but an example. Don't know if any of you have ever fired a rifle before, but if you have, you know the bullet leaves the barrel of the gun at a very high rate of speed, okay? But the mass of the bullet is very, very, very small, okay? So the momentum before you pulled the trigger was zero. The rifle is just there. But as soon as you pull the trigger, that bullet goes flying out this end at a very high rate of speed, but a very low velocity, mass. That's the momentum of the bullet. Now, if you've ever fired a weapon, you'll know it kicks. And some of them kick really big time, okay? Well, that kick is the force of the entire rifle, that's its mass, times its velocity as it bumps into your shoulder. And by the way, folks, if you ever do fire a weapon, you better hold that weapon snug against your shoulder. If you hold it off your shoulder, you're going to have a very bad bruise on your shoulder. You may even have a dislocated shoulder. You hold it right up against it, and here's why. Because the momentum of the bullet going this way has to equal the momentum of the rifle going this way. That rifle has a certain mass, so it won't go as fast as the bullet does because it's a lot more massive than the bullet, but it could still pack a pretty bad punch, okay? So what you do if you hold it right against your shoulder, you become part of the mass. So it's not just the rifle's mass, it's your mass plus the rifle mass, and that decreases the velocity significantly, so the recoil is not nearly as bad. So that's conservation of momentum. Here's how we phrase it. The total momentum of a group of interacting objects remains the same in the absence of external forces. Remember, that's how we talked about Newton's first law, absence of external forces, no external forces. Now, let's give a few other examples. Now, this you may find very hard to believe, but it is absolutely true. I'm guessing that some of you, if not all of you, have played pool or billiards before, right? How do you start your game? You put the rack down there, and what is it, 15 balls in the rack? 1, 2, 3, 4, 5, 6, whatever, okay? You have the balls all racked together in that little triangular shape. You have one cue ball, okay? Whoever is breaking it, he or she hits that cue ball, usually pretty much as hard as they can, hitting against that rack, and those balls fly everywhere on the table, right? Well, guess what? The initial momentum of that system is whatever the mass of that cue ball is times the velocity of the cue ball, going down the table in one direction. As soon as it hits the others, they fly everywhere. Some go to the right, some go to the left, some bounce backwards, some go forward. If you were to add every one of those momenta up, you would get the same momentum as that one cue ball going down the table to begin with. Believe it or not, that's true. But remember, momentum is a vector quantity. So for every ball that goes to the left, one of them goes to the right because the momentum is equal. Okay? For anything that goes forward, you'll have a few coming back toward you. The net force, the next momentum is forward because that's where the cue ball was heading, but some of them do bounce back this way. So they are all over the table because of conservation momentum. Okay? Now, Other places you have this, collisions. Now, I hope none of you have ever been in a collision before, but I can remember it was so memorable. My first, when I was a freshman at Georgia Tech, I had been there a week for orientation or close to it, something like that. And then my brother, who was a junior, he came up, some of his friends came up. Now, we didn't have a car there, but one of his friends did. And they decided classes hadn't started yet, let's go see a movie, okay? I remember the movie as well. It was Easy Rider, classic movie. Y'all probably never heard of it, but Peter Fonda and Jack Nicholson, I think, were the stars of that movie. That was back when no one knew who Jack Nicholson was. That was before he was famous, okay? In fact, Easy Rider probably gave him his fame. So we were going to the Capri Theater in Atlanta to see Easy Rider, okay? Frank Michelle was driving. My brother was trying to navigate for him, and I was in the back seat. Well, they were trying to find where the entrance to the theater was, and Mike said, oh, there it is, you know, and pointed like that. Well, Frank just immediately reacted and turned right in front of an oncoming car, okay? What they did then, when the police showed up, we missed the movie, by the way, but when the police showed up, they measured the skid marks because that was the best way they could determine what the velocity of the oncoming car was, what the velocity of Frank's car was. They did the best they could, and they had to use things like the coefficient of friction for the highway, for the road, stuff like this. So they do use conservation momentum in analyzing collisions, okay? They also use it in analyzing action-reaction interactions, okay? Is that enough action there? Action-reaction interaction, okay? Remember, that's basically Newton's third law, action-reaction, okay? And I can't remember if I gave this example before, but this is a pretty tragic one. I think it was the 1996 Olympics. I think they were the ones held in Atlanta, the 100-year Olympics. And they, I believe it was the Summer Olympics when the gymnasts were participating. And one of the very young-looking Chinese gymnasts went racing down the female gymnast. They do a thing called the vault, racing down this runway there, and then hitting a thing that flew her into the air, and then she did a somersault on a pommel horse, but she lost her balance, okay, unfortunately. And she didn't land on the padding, she landed off the padding. I think she became either paraplegic or quadriplegic because action-reaction, she hit the floor at an enormously high rate of speed. The floor hit her at an enormously high force. We'll talk about this a little bit later. But these are what we have for conservation momentum. Momentum is conserved, forces are not, so we can use conservation momentum to analyze all kinds of activities, motions, and that's its advantage over forces. Now, this is what I was alluding to before, the concept. Okay, wait, before we go there, let me back up one. On page 47, under conservation momentum, let's go back one. And this is exactly what's written here. The total momentum of a group of interacting objects remains the same in the absence of external forces. That's the definition, basically, of conservation of momentum. Okay. I had forgotten that was here. Okay. Now let's turn the page to impulse. But before we get to impulse, there are a couple of examples. So let's do the examples under conservation momentum. What I think I'll do is go to the whiteboard and do it there. Okay. Let me get my pad here. Wrong. There it is. I couldn't find my stylus. Okay, example 214, page 48. Now, my pictures really stink. You probably already seen that. Before I get to drawing, I'm going to try to move some things around because they put these taskbars that block the white space, and that gives me less room to write. And then they also put the taskbar, the white space, beneath or behind some of the things that Zoom puts out there with your names on it. So I try to move everything to get it most white space possible. Okay, here we go. A 20,000 kilogram railroad car. Okay, now I don't draw these well, so bear with me. Oh, this is supposed to be level. It's not. Okay, here's the railroad car. Okay, there's a railroad car, not very well drawn. It has kilograms, measures what? Mass of the railroad car is, this pen is not writing well, 20,000 kilograms. Okay, let's call this railroad car A. Mass of railroad car A. The pen is not writing well. Is coasting at a velocity of 3 meters per second. The pen is not writing well. 3 meters per second. That is a velocity, right? Meters per second, velocity. When it collides with and couples with a second identical car at rest. So this car over here is exactly the same size, exactly the same mass. Doesn't look like it, but let's pretend that it is. And these have couplings on them, okay? And when they combine, they collide. Now this one's at rest. What does at rest mean? Initial velocity for, let's call this B, okay? This is car B. I said A. And the mass of B is identical. The mass of B is also 20,000 kilograms. They're identical. The difference is initial velocity of B is 0 because it's at rest. This is initial velocity of A. That's 3 meters per second to the right. Okay? Now, when they collide, they couple with each other, meaning they stick together. Okay? So they couple. What is the resulting speed of the combined cars? So this is your initial momentum of the system, the entire system, and this is a vector quantity. This is a vector. This, of course, is 0 vector. It doesn't have anything. So the initial momentum of the system here is the mass of car A times the velocity of car A, that's the initial velocity of car A, plus the mass of car B times the initial velocity of car B. But this is 0, so this has no contributing. So the initial momentum of the entire system is 20,000 this thing keeps popping up stupid stuff here, kilograms, this pen is not writing well at all, times 3 meters per second. So the initial momentum of the system here is 60,000, and then use your units, kilogram, the pen is not writing well, meter per second. That's your unit for momentum. That's the initial momentum of the system. Okay? Now, after the collision, and they couple together, the momentum is conserved. It cannot change. Now we're assuming we have no friction on the railroad tracks here. That's not probably a great idea, but it's pretty close because railroad cars, those tracks are really smooth, so there's not much friction. So we'll not count any friction. But what's the final momentum of the system? P final here, that's also a vector quantity. because momentum is conserved, it has to be 60,000, the pen's not writing well, kilogram meter per second, because momentum is conserved. But after the collision, now these two are stuck together. They were both 20,000 kilograms, so the mass of the system, okay, times the velocity of the system. This is what we're looking for. You could call that final velocity if you wanted to. Okay, well, the mass of the system now is 40,000 kilograms. Times V final. Okay, final velocity of the system. That's what we're looking for. What is the resulting speed of the combined cars? So, to get this, you divide both sides by 40,000. Kilograms. Okay, divide this by 40,000 kilograms. Both sides of the equation by that, and everything goes out here except V final. So this is your final velocity. And what does this? Well, these zeros, you can get rid of all those. 4 up there, 4 down there. 6 divided by 4 is 3/2. And the kilogram cancels out kilogram, and that leaves you meters per second. So this would be 1.5 meters per second. And that sort of makes sense, doesn't it? Because it started at 3 meters per second, doubled the mass, so it halved the velocity. And sure enough, it was 1.5 meters per second. Now, here's the weird thing, and I don't know why they did this, okay? They wrote this answer as if it was 2. They said we only have one significant digit here, one significant digit here, one significant digit here, one significant digit here, one significant digit everywhere, so they round this to 1. Look to the right, and that's a 5 or more, bump it up to 2. That makes no sense, okay? They should have made this 60 and put a bar over it, 20, put a bar over it. This is 3.0. Now, was that someone coming in, or was that just my random mark across? Okay, we up to 12 students now. Let's see what I've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I've got all 12. Good. All right, hopefully a few more will be coming in. I think we got a total of 16 in the class now. Or we did. Okay. So, it doesn't make any sense to call that 2 meters per second. That's not conserved. Half of this is 1.5. So I would have done 3.0 here and made that 1.5. But the book does weird things sometimes. Okay. Now that was example 2-14. Let's move. Any questions on that before I delete it? Oh, here comes Valerie. So she must have had to bump out and come back in. Okay. And she's coming in under her name now rather than her telephone, so that's good. All right, any questions on 214? Let's move to 215. Okay. Also on page 48. Okay. A student and her rowboat have a combined mass of 100 kilograms. So here's the surface of the water. That's supposed to be level. Okay, it's not. It's sort of wavy out there, isn't it? And the student in her rowboat, oops, that's not very good, is it? Here is the rowboat, and here's the student sitting in a rowboat. Okay, whatever. And I'll even show a paddle, the rowboat doing the paddling. Okay, combined mass, so the total mass here, mass total, is equal to 100. Now, last time they had one significant digit. This time they have 4 significant digits. That's, I mean, it's just sort of crazy. 100.0 kilograms. Standing, so here she's going to stand up, not going to sit down like she should, in a motionless boat, that means initial velocity of that boat is 0. Motionless, no velocity. That would be in meters per second. Okay? She tosses, so she's going to throw a 5-kilogram rock out the stern. Okay? She's in perfectly calm water. She tosses a 5-kilogram rock, so the mass of this rock is equal to 5.0 kilogram. Now that's only 2 significant digits. Okay? Tosses it out the back of the boat with a velocity, so its velocity, V for the rock, is 5.0 meters per second. 5.0 meters per second. Now don't think that the numbers have to be the same, they just happen to be in this one. The question now is, what will be the resulting speed of the boat? Okay? Now, remember it was at rest, initial velocity 0. Maybe she lost her paddle. That may be the problem. So what she's done, she's got the boat heading to shore, and she picks up a rock that she happens for some reason to have in the boat, throws it out the rear of the boat, and when she does that, the rock goes this way with a certain momentum, the boat goes this way with an equal but opposite momentum. So what we have to figure out is what the momentum of the rock in this direction is to find out what the momentum of the boat is. Once you know the momentum of the boat, you can get the what would be the resulting speed. So we're looking for V final here. That's what we're looking for. So let's do initial velocity, initial momentum of the system. P initial for the system is 0. Okay, they're not moving at all. Okay, P final for the rock is going to be mass of the rock times velocity of the rock. Okay, mass of the rock was 5.0 kilogram times velocity of the rock, once she threw it, was 5.0 meters per second. So now the momentum of the rock at the end was 25 kilogram meter per second. Multiply the numbers, multiply the units. Now you don't put a 0.0 in there because you only have 2 significant digits here, 2 there, here's your 2 here. Don't put a decimal in anything else. Okay, well, the boat was initially at rest, but now you gave the rock a momentum in this direction. That means the boat has a momentum in this direction. So the momentum of the boat with this passenger has to also be, and I'm going to put this as a minus 25 because it's going to the left. We'll make this a plus 25 here, kilogram meter per second. Okay, in the right hand direction, because this is a vector quantity. Well, this has to be equal to the mass of the boat times the velocity, the final velocity of the boat. Well, the mass of the boat is still 100 kilograms. Now, I found that a little disingenuous there, but we'll let them get away with it. 100 kilograms, because she had the rock in the boat to begin with, but we're going to ignore that, times V final of the boat. Okay, and that has to equal 25 kilogram meter per second. Okay, so we'll divide both sides by 100 kilograms. Keep up with your units here. We'll divide this by 100 also, kilograms. So everything here goes out except V final, that's what we're looking for. Here only the kilograms go out, and this gives you 0.25 meters per second. So that is your final velocity of the boat, because we divided out the mass. Okay, so she's not going fast, but she is going slowly to shore now. Hopefully she threw it in the right direction so that she does go 0.25 meters per second. And as long as, excuse me, not too much friction, and water does have friction, she will inch her way toward shore. Okay, however, it may not be strong enough to get her there because there is friction in the water. All right, sorry, I think I told you before, I'm really low in red cells, so let me get a little bit of a boost here. I don't know if sugar water will do that much good, but a little bit of caffeine, it can't hurt too much. All right. Any questions on 2.14 or 2.15? Okay, let's go back to Chapter 2 PowerPoints. Okay, we'll return to the original slide. That was our conservation momentum. Both of those examples were. Let's move on to impulse. Now, impulse is a really interesting concept, and what impulse is a force acting on an object over some time period, for some time interval. I like to call that delta t. The book just calls it t, but it's not time of day type thing. It's a time interval, delta t. Now, here is a key statement. An impulse produces a change in momentum. That's the key here. Okay? Now, let's go back to what Newton was talking about when he said his quantity of motion. Okay? Momentum, vector quantity, is equal to a mass times a velocity. Mass is a scalar quantity. You don't put an arrow over it. Velocity is a vector quantity. You do. Now, Newton worked with change. That was his big deal. That's why he developed calculus. That's why he did with his laws of motion. He was dealing with instantaneous change. Okay? So what we're going to do is do the time rate of change. How much is the momentum changing over time? Okay? Well, we'll divide both sides by that delta t. The book just calls it t, but that's your time interval. Okay? I like to call it delta t. Okay? So this is a time rate of change of momentum. Okay? And this is a mass times velocity over time rate of change of, over your time interval. Okay. Mass doesn't change in time. Velocity does. Mass stays the same. So what we have here is a change of momentum. If I could get my pen to show up somewhere here, where is it? There it is. Okay. If we were to do this, this is, let's multiply both sides of the equation. Well, let's see. Okay. Let's actually deal with this. Okay. This is mass. That doesn't change over time. And what's the change of velocity over time? That is acceleration. Well, guess what this is? Your change of momentum is another way to talk about your force. Okay? That's what the time rate of change of Newton's quantity of motion, momentum, that's where you get Newton's second law. Okay? Newton didn't refer to, I don't think, in terms of mass times acceleration. He referred to it in the time rate of change of momentum, or his quantity of motion. Okay. Now, so what we're going to do here is multiply both sides of the equation. If I can get my pen to show up again. Boy, this pen just keeps, oh, there it is. Okay. Let's just sort of forget this for now and multiply both sides of this equation. Where in the world is it? There it is. By delta t. Okay. Multiply this by delta t, that time interval. Well, here the delta t's go out, And what we have is a change of momentum is equal force times in a time period. That's exactly what it says here. A force acting over some time period, F times delta T, that gives you a change of momentum. That's what impulse is, change of momentum. Now here is where we get our other name for momentum, because that is a change of momentum. Well, a force is measured in, where is my pen? There it is, okay. Force is measured in Newton, and the time period is measured in second. So you can use the term for momentum as Newton second. It's either kilogram, meter per second, or it's a Newton second. Either one of those are equivalent. Okay, so either one you want to use, Newton second or kilogram meter per second. I said it didn't have its own unit, but it has a compound unit, but this one's a little easier to deal with than that one. Okay, now let's go back to that gymnast. Okay, well, let's pick something a little better. Okay, maybe to begin. Well, let's start with the gymnast. We already mentioned her. When she hit the floor, she had an enormous change of momentum because she was going at a very high rate of speed. I can't find my pen. Where is it? There it is. A very high rate of speed here, velocity. She had a certain mass, but when she hit the floor, the time interval in hitting the floor was almost instantaneous. So if this is a significant change of velocity here, which it was, she went from going very fast to stop in almost an instant. That made this force incredibly large. Okay, so let's back up a little bit. Y'all probably can't remember this, okay, but I can remember the earliest vehicles that my parents had when I was growing up. This is long before airbags, long before seat belts, long before anything there. Believe it or not, those cars back in the day, they had a metal dashboard, okay? And especially on the passenger side, that metal dashboard poked out at you. If you were ever in an accident, they called that passenger side the death trap, the death seat. Why? Because you were going to hit that metal dashboard at a very high rate of speed. Because if you're driving along at the mass of the car, if I could find the, oh, here it is. The mass of the car was huge. The velocity of the car was pretty fast. That gave you a huge momentum. And then when you hit the tree, hit the rock, hit the whatever it was, hit another vehicle, suddenly you went to a sudden stop here. A very big MV here going to 0 MV here. That's an enormously high change of momentum. Now, if that happened over a very, very, very short time period, think almost instantaneous, the force had to be huge. If this delta T was very, very small, the force is astronomically large. And that's why the person in the passenger seat, they called it the death seat, because so many times that person didn't make it. Or if they did make it, their broken bones, broken collarbones, broken cheekbones, I mean, they were in terrible shape. Okay? Now, I can remember maybe for many years we had a pickup truck, and that was about all. My father was a farmer. But after a while, he did buy a little Plymouth. I can't remember what the name of the car was. It wasn't a Fury. It was a Galant, or I can't remember what the name of it was. But that was the first car we had that had a padded dashboard. Still metal underneath the pad, but it had maybe an inch or 3/4 of an inch of padding on it. Okay? Now, that doesn't seem like a lot, but if you think about that, when you had that same change of momentum here, that big mass of the car, which I can't get, where is it now? I can't find my pen. I'm making marks all over the place. There it is. Okay. Very massive car, high rate of speed, change of momentum, going from a high rate of speed to 0. That's a big change of momentum here. But now the time interval is a little bit longer, because now you had to compress the foam in that before it sprung back. So let's say it went from a thousandth of a second to a tenth of a second for that change of momentum. Well, that was 100-fold increase in time interval. That meant 100-fold decrease in the force. So sure enough, the force was much, much less. Not enough less, but it was less. Okay? Now, the next improvement they had on car safety were seat belts. And of course, at first it was just a belt, no shoulder harness, just a belt. What did the belt do for you? It kept you attached to the seat, so when you did have that huge change of momentum that now I can't get my pen back. Where in the world is it now? I don't know where it is. Come on, pen, where are you? There we are. Okay. Big change of mass times velocity. Okay. Now the seat belt threw you forward but pulled you back. So now the time interval on which it took you to stop is much, much longer. Maybe even, rather than a tenth of a second, maybe 5 seconds. So that's a 50, no, yeah, a 50-fold increase in your time interval. That's a 50-fold decrease in the force. Suddenly things were getting a lot better. Okay, so then after that they put the shoulder harness on, and the shoulder harness took even more time for you to hit. Okay, so the time interval increased, the force decreased. Okay, and then finally they came out with airbags, and airbags really lengthen the time interval over which that occurs. In fact, they explode right when you hit, and your face goes into the airbag and then comes back out. A great deal of time, larger time interval, much smaller force. In fact, quite often there's no injuries. Even when you're going at a fairly high rate of speed and the airbag deploys, as long as you're not going too fast, you can usually escape with very minor injuries there. Airbag. Same thing goes for padding. Remember the gymnast? If she had landed on the padding, then she probably would have survived without being a quadriplegic or a paraplegic. Football players, what are they doing all the time now? They're trying to improve the quality of the helmets so the impact, the time interval over which your brain, the head, hits on those really hard hits there, and that's why they've done away with targeting. Okay, and they really come down hard on that. The more padding you have, the longer the time frame for that change of momentum to happen. The longer the time frame, the less the force. Okay, you put padding on your knees, your elbows, your helmets. Okay, now I can remember in the old days when they put up, say, a highway overpass. They put metal guardrails. Hey, not a good idea, because a metal guardrail, that's going to have a very small time interval. If you hit the guardrail, the force is going to be enormous. Nowadays they have either cushioning in there, or sometimes plastic barrels and things like this, so now the time interval is a much longer time interval, reducing the force, so the impulse of your collisions the impulse is the same, change of momentum. What's that again? Okay, all right, so your impulse is the same, but the force is much reduced if you've increased that time interval. Does that make sense? Sorry that my slide is all covered with red ink now. Okay, so let me clear some of that red ink out of the way so you can read better. All right, so here we have it. Force is time rate of change of momentum, delta P over delta T. I like to put the delta down there. This is P final minus P initial over that time interval, T final minus T initial. Okay, well, if that initial momentum is, say, 0, or the final momentum is 0, you've hit the guardrail or whatever it was, so your final momentum is 0, your initial momentum, this is your impulse. Okay, well, this isn't quite, but it's close to it. If you multiply both sides by T, for a given change of momentum here, the larger the T, the smaller the F. The smaller the T, the larger the F. That force is what hits you. That's what breaks bones. That's what causes the problems. Does that make sense? There's impulse. Okay. Whoa. All right. Now, the next topic, 2.8, is forces and circular motion. This picks up on page 49. Now, there is a little concepts applied here, momentum experiment, and you may have seen these before. Have you seen these? Sort of a little desk toy that people will have and has, say, 5 balls hanging from strings. Okay, you pick up one ball, release it, and it hits the other 4, and only one ball kicks up, comes back, kicks one, comes back, kicks one. One ball moves, the other 3 stay perfectly still. Okay, conservation momentum. Another thing you could do is pick up 2 balls, okay, and then release those, and when they hit, the 2 end balls go up, that middle one stays perfectly still. Conservation momentum. Or you could pick up 3 balls here and only leave 2 here. When you release the balls here, they hit, 3 balls go up, 2 stay still. Conservation of momentum. Or you could move all 4 balls up here, leaving just 1 down here, and when you release it, they hit, 4 balls move up here, and 1 stays here. Conservation momentum. So that's a little momentum experiment. If you've seen one of those devices, they're sort of fun to play with. Okay? If we were doing labs in class, like I wish we could, but we can't, that was one of the things we would do. We would be rolling balls down a track and watching the momentum being conserved. We can't do that. I looked for a momentum experiment in the simulations. I couldn't find any. So we're going to be doing, instead of that, we'll be doing forces and circular motion, which is what we're doing in 2.8. Okay. Now, circular motion is accelerated motion. Wait a minute. What if you're not changing speed? Is that accelerating? Yes, it is, because if you're moving in a circle along a curve, your direction is always changing. And remember, velocity is a vector quantity. Velocity is changing if you're changing speed or changing direction or changing both. So yes, that's accelerated motion because your direction is changing anytime you move in a curve. Now, that motion is called, that accelerated motion is called centripetal acceleration. Okay? Centripetal means center, you can almost see the word there, seeking. I don't know what pedal means, but that's what it means, center seeking. The acceleration is always toward the center of that curve. Okay? And you know that to be true because if you turn around a curve real quickly, you tend to fly out of the curve unless your tires hold and push you back into the curve. Center seeking acceleration. Centripetal force must be acting. If you have a centripetal acceleration, you have to have a centripetal force. Now, a lot of times you'll hear people talk about a centrifugal force. That's an apparent tug outwards as your direction changes, but that's not a real force. That's just your momentum trying to keep going in the same direction. Your inertia trying to keep you going in the same direction. That's not a force. That's just the result of inertia. Okay? Centripetal force ends. When it does, then you have straight line motion. Now I can remember, or I can easily imagine, I don't remember actually doing this, but I bet you can picture this. Get you a rock and tie it on a string, right? Tie it really well on the string. And then take that string and twirl it around your head. Okay? Where is the rock going? It's going in circular motion around your head. Okay? Now, if you were to slip and release the string, or the string were to break, that rock no longer moves in circular motion. Here's Dre again, so he must have had to jump out and come back. I think I've already got him here. Let me make sure. Yes, I do. Okay. So, if the string were to break or it would slip from your fingers, the rock no longer goes in centripetal motion, center seeking, it goes straight line motion. It always heads toward a window. I don't know why that's true, but always heads toward a window. Straight line motion. Okay? Hopefully you haven't experienced that, but many of us probably have. Okay, I can't get it to advance until I click on the slide. Okay, so this is what it's talking about. If you're moving in a circular path here, your velocity is always changing. Here your velocity is tangent here it's tangent there, here it's tangent here it's tangent there. Always changing the direction of your velocity. That's acceleration. The acceleration is always toward the center of that curve. Okay? And that's your centripetal acceleration. Therefore, your centripetal force will be in that same direction, because force is mass times acceleration. Acceleration is your vector quantity, force is the vector quantity, so it goes in that direction. Your velocity is trying to take you this way, but because of the force pulling you this way, you move in a circular path. Okay? And that's what's happening with forces in circular motion. All right. Before we move to Newton's law of gravitation, let's do example 216 and 217. But before we do that, let me write down the formulas that we used here. Okay? If I can find my pen again. This thing is so elusive. There it is. Okay, I see it now. Your centripetal acceleration is defined this way: v squared over r, where r is your radius, v is your velocity. Okay, v squared over r. Now I think I told you earlier in the term that a lot of times when your primary variable is squared, you're going to precede that with a coefficient of 1/2. This is the one example that doesn't happen. Okay, and I wish I could find, there it is. Okay, you don't have a 1/2 in front of that. It's just v squared over r. Okay, well, what's your force then? Force, centripetal force, is mass times centripetal acceleration. Both vector quantities here, so your centripetal force is m v squared over r. That is the magnitude of that centripetal force. Okay, you just multiply the mass times acceleration, just like we did for Newton's second law. Okay, with that in mind, those are equations 210 and 211, top of page 50, left-hand column of 50. So let us now go to our whiteboard. Okay, all right, to clear that. Okay, a 0.25 kilogram ball, 0.25 kilogram ball. What's that a measure of? The mass of the ball. Okay, scalar quantity is attached to the end of a 0.5 meter string. So 0.5 meters is your string. Well, that's going to be your radius. Okay, because that's what your do. It's moved in a horizontal circle at 2 meters per second. What is 2 meters per second? That's a velocity. So that's your v. Okay? Now, what is the net force needed to keep the ball in its circular path? So the net force needed would be the centripetal force. And centripetal force that we just did was the mass of the ball times the acceleration, centripetal acceleration, which is v squared over r. So this is going to be 0.25 kilograms times v squared, which was 2 squared, which would be 4.0, but square your units as well. Meter squared per second squared. You square not just the number, but square the units as well. Divided by r. Your r was 0.5 meters. Okay? Keep up with your units. They are your friends here. Okay? Now, that is a square there. It looks like a cube, but that's a square. Okay? Meter squared per second squared. Well, one thing, this meter is going to cancel one of those meters out, leaving you just a meter. Okay? Now, I'm going to do something a little bizarre here. I'm going to multiply the denominator by 2 and the numerator by 2, because 2 over 2 is 1. That's legal. 2 times 0.5 is going to be 1. Okay? So your denominator becomes 1, and when you multiply this, 2 times 4 is 8, and 1/4 of 8 is 2 newtons. Kilogram meter per second squared, that's a newton. A great unit for force. 2 newtons. And that's exactly what they got. Now, what if we make the string in example 2 that we just did here, I don't know why they say example, 2.16, I couldn't read that, is 1/2 as long. So now let's do this in a different color. Y'all give me a new color. We've got, let's not use white, you won't be able to see that. We have purple or lavender, we've already used black. We have red, pink, or brown. We have yellow, say again? Red. Okay, we'll do it in red. So now we're going to have a new radius that's half as long. That's 0.25 meters. Okay? What is the force that's now needed? Well, now the centripetal force will be mass of the ball or rock or whatever it was. Yeah, it was a ball. Okay, times velocity squared. We're assuming that's going to be the same, but what we're going to do is decrease the radius to the new radius 0.25. Okay, so this will be 0.25 kilogram, same as before, times velocity, same as before, 2.0 meters per second, but we're going to square it, so that's going to be 4.0 meters squared per second squared. Keep up with your units, they're your friends. But now the radius is going to be 0.25 meters. Okay, now notice here, one of the meters cancels one of those meters. Good. Now this 0.25 exactly cancels that one. We don't have to multiply by anything, so what do we have? 1 times 4 is 4. And this time we could put 4.0 newtons. Why? 2 significant digits there, 2 there, 2 there, 2 everywhere, so you could do this as 4.0 newtons. The other one we had to leave as 2 newtons because you only had 1 significant digit there. Again, they're being sort of nitpicky about it, but that's why they did that. So, shorten the string, you increase the force that you have to do. Okay? And I think you probably realize that if you've ever swung a rock or a ball on a string. If you have a long string, it doesn't take that much force to keep it going, but a shorter string, you got to do it a bit harder. Okay, and that's why. Okay, that finishes 2.17, sorry about that. So let's go back to the PowerPoint. Okay, so that was forces in circular motion. Now let's move to Newton's law of gravitation. I think I said it wrong before. This is what today's lab is going to be, Newton's law of gravitation. Okay? Now, before this, everybody knew that things fell to the ground, but they didn't know why. Isaac Newton, brilliant man that he was, not only did he come up with 3 laws of motion, not only did he come up with a brand new field of mathematics, the calculus, not only did he explain why planets move around the sun and describe that really well, this was part of his Newton's law of gravitation. Now supposedly he came up with the idea watching the apple fall from the tree. I don't think it hit him in his head, that's how they always did it, but he got to thinking about it that way. Okay? And Newton's law of gravitation, gravity is always, always, always an attractive force. Okay? Never repulsive. I wish I could find my pen. I cannot find there it is. Okay, there it is. It's always, well, there it is. Okay. Always an attractive force. Never repulsive. Later, when we talk about electricity, sometimes it's repulsive, sometimes it's attractive. When we talk about magnets, sometimes it's repulsive, sometimes it's attractive. Gravity, always, always attractive. Between all masses, okay. Now, sometimes we don't notice that, okay. For instance, if I were walking down the hallway and you were walking the other way, we aren't suddenly attracted to each other because of law of gravity. We are, but it's such a weak attraction, we don't notice it. When we do the lab today, we'll see you have to have very massive objects before you get measurable attraction. So that's what we'll be dealing with today. Now, it's proportional. The law of gravitation is proportional to, where is my pen now? This is so bizarre. It just disappears on me. There it is, right there. It's proportional to the product of the masses. So the force due to gravity, I'm going to call that F sub g, is proportional to the product of the masses, m1 times m2. Hang on to these concepts. We're going to be using them in today's lab. Okay? It's inversely proportional to the separation distance squared. Okay? So it'll be inversely proportional to r squared, where r is the separation distance. That's a proportionality. Okay? Now, to make it an equation, we do F sub g is equal to some constant. And the constant they use is the universal gravitational constant times m1, times m2 divided by r squared. Sorry about that. That got off there. Now, they say here it explains why the acceleration due to gravity on the surface of the Earth is 9.8 meters per second squared. Let's see if we can figure that out. Okay? Now, let's do a little bit more work before we come back and do that. Okay? So, I'm going to remove my scratch here. Okay? Here is one example of this. The moon is going around the Earth. There is its velocity this way. It wants to go this way, but the Earth keeps pulling it inward. That's just like that string, okay? The acceleration due to gravity, the centripetal force, that's what keeps the moon in orbit around the Earth, okay? It's always falling toward the Earth, but not crashing into the Earth because it still has a velocity perpendicular to its fall, okay? So that's one example. The Earth going around the sun, every other planet going around the sun, they all are held in place because of that gravity, okay? And the sun is really, 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 really massive. The Earth is massive. The moon is massive. That's why you do sense it then. One ball rolling past another ball, you don't even notice they are attracted at all, okay? Now, let's go back and do I'm trying to figure the order I'm going to do these. Okay. Let's do example 2.18 first. Okay. Now, I think I'll go to whiteboard again. If I can find, if I hold my pen too close to the one board, the other thing doesn't work. So let's go back to the whiteboard here. Okay. And let's clear the drawing. Okay. Now, you want to go back to black or leave it red? Doesn't matter to me. Anybody? Leave it red. Okay. Example 2.18. What is the force of gravitational attraction between two 60-kilogram students? Okay, now that's not very massive, 60 kilograms. So M1, student number 1, is 60.0 kilograms. Student number 2 is also 60.0 kilograms, the mass of the two students, okay? And that, by the way, is about 132 pound students, so not huge, but, you know, decent, okay? They're standing 1 meter apart, so your distance between them is 1.00 meters. 3 significant digits here, okay? Now, here's the part that I was debating on. Remember when I said the formula and gave the coefficient, or what do you call it, proportionality constant. Remember it came up being F, force due to gravity, is, I said universal gravitational constant times M1 times M2 divided by the distance squared. Okay, this is so aggravating. Distance squared. Okay, now what is that gravitational constant? They mention it here in the book. They don't do a big deal about it, but here's what it is. It's 6.67, okay, times 10, this is scientific notation, times 10 to the minus 11 Newton meter squared, my pen is acting up, divided by kilogram squared. Weird units on it, but that's what it is. But notice how terribly tiny that number is. That's 0.0000000000667. That's a very, very, very small number. So in order to have any attraction at all, these masses have to be incredibly large. And that's why 60 kilograms just isn't going to hack it. And we'll see. Let's do it. F sub g, force due to gravity, is this 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. That's your proportionality constant, times 60.0 kilograms, that's the mass of the first student, times the mass of the second student, 60.0 kilograms. They have the same mass, remember, by 132 pounds if you're dealing with force, okay, divided by 1.00 meters, distance apart, squared. Okay, now let's deal with the units first. Here we have meter squared here. Here we have meter squared there. Here we have a kilogram times a kilogram, and here we have kilogram squared. Guess what? All that's left is Newton. That's exactly what we measure force in. So that makes sense. Now, here's the part. Now, I don't know where y'all are in your calculator, I want to say etiquette. That's not really the best word. How in the world do you operate your calculators? Now, let me just ask you, do most of you actually have calculators, or are you using a phone like I am? In the phone. Okay, or a calculator on the computer. Okay, now I'm going to bring up mine on my phone, so I'm going to press the calculator keys. Okay, when you have it like this, that's a simple little calculator. All it does is add, subtract, multiply, and divide. We're raising things to exponentials. You don't have that on here. So you turn your calculator sideways, or your phone sideways, that becomes a scientific calculator. Okay, now I don't know if you're familiar with this. This is scientific notation. Now my calculator, I don't know if you can see it, you see that symbol right there that says EE. That's your exponential. Some of you may have on your calculator EXP. Does the same thing, okay? But I have EE or EXP. That's what we'll use. So here's how I'm going to punch it in. Okay, 6.67. Come on, get up here. Okay. Uh-oh, I just messed with my volume. Sorry about that. Okay. 6.67. And then don't do times 10. Do not do times 10. Hit that EE key or EXP key, and nothing seems to happen at first on mine. If you have a calculator, you may see two little digits show up. Okay. Then we do minus 11. On my phone, I can't do the minus first. I do the 11 first, and then change the sign to make it a minus. And you see that change sign key, plus minus key right there. That's what I'm going to press, and that makes it a minus 11. Okay, so I've got 6.67 EE 11 minus. Now, if you have a regular calculator, you probably are going to do 6.67 EE or EXP, and then you'll hit the key that has a minus sign in parentheses. That means you're using a negative, not your subtraction key. Your subtraction key is a subtraction. The minus key in parentheses is your negation key. You would hit that first and then type 11. But on my phone, I don't do that. I have to do 11 first and then change sign. Okay, so that's 6.67 EE 11 minus. Then multiply that by 60, multiply it again by 60, okay, and then I'm going to divide by, and I'm going to show you this in gory detail now. Here it's just dividing by 1, because 1 squared is 1, okay? But when we do the lab, we're going to be dealing with way bigger numbers than that. So when I'm dividing by 1, I'm going to open my parentheses, that's right over here, okay? And then type in a 1, which is sort of ridiculous, and then close the parentheses and square it. My squaring key is right here, So I'm going to press that square key, and that's just 1, and then press equal. Look at that number. The force is 0.000000240. That is an incredibly small force. Do you think any of you are going to feel that force if you're walking down the hall? No way at all. And here's Gerald. I can't remember, was he here before or not? Yes, he was. He was here before. Must have just come back. Okay? Now, so what is our answer here? The force due to gravity is, now I'm going to change it back to scientific notation. Move that decimal all the way past the 2.40. Now I'm going to stop there because this is 3 significant digits. That's 3, and this is 3. So 2.40, the next digit is a 1, that's less than 5, so I'm going to leave that alone, times 10. Okay, now I'm going to count how many decimal places I have to move the decimal from here to after the 2. So that's 1, 2, 3, 4, 5, 6, 7. 10 to the minus 7, because you moved it to the left, minus 7. And what were the units? Newtons. Okay. Do any of you think you can feel a force of 2.4 times 10 to the minus 7 newtons? Not me. Okay. That is such an incredibly small force, you don't even sense it. Not at all. And that's what they get in the book, 2.40 times 10 to the minus 7 newton. Okay. Now, you would not notice that force. In fact, it would be difficult to measure such a small force. Okay. Now, the next thing we're going to do here, I think, let's just see where we're going from here. Let's go back to our PowerPoint. Okay, and resume the slideshow. Why in the world it won't show the, okay, there we go. Okay, it says this explains why G is 9.8 meters per second squared. Not quite ready, but awfully close. Okay, so what we do is go to example 2.19. Okay, now, so let's go back to our whiteboard. Okay. And I'm going to clear the screen unless you want it up there any longer, do you? Okay. Now, 2.19. The surface of the Earth is approximately 6,400 kilometers from its center. Okay. I'm going to put my calculator down for a moment here, the phone. Okay. So I'm going to try to do a representation of the Earth. Okay. Let's just say that's the Earth. So the distance from the center of the Earth to the surface of the Earth is 6,400 kilometers. This radius here is 6,400 kilometers. Now, most of the time when we're doing SI units, we don't deal with kilometers, we deal with meters. Well, this would be 6.40, I don't know how many significant digits they have, no, it's 6.4. So 6.4 times 10 to the third kilometers. Okay, but guess what? A kilometer is 10 to the third, so this would be 6.4 times 10 to the third times 10 to the third is 10 to the sixth meters. 6.4 million meters from the center of the Earth to the surface of the Earth. That's your radius. What we have been calling the distance. Okay, so hang on to that thought. Okay, if the mass of the Earth, and here is the mass right here, the mass of the Earth is equal to 6.0 times 10 to the 24th kilograms. Wow, talk about a big number, times 10 to the 24th kilograms. Okay, what is the acceleration due to gravity g near the surface of the Earth? So what we're looking for is g. Now we know what it's supposed to be. Let's see what we calculate it to be. Okay, now the force due to gravity, F sub g, is equal to what we had before, that capital G times m1 m2 over d squared. Remember, that's our formula. Okay, now one of these masses is the mass of the object. I don't care which one you call it. So this, by the way, that force due to gravity is, let's call it m1 m1g. Okay, so m1g is equal to g times m1, and this second mass is the mass of the Earth, so I'm going to put mass of Earth there, divided by d squared. Okay, well, the first thing we're going to do is divide out the m1s, okay, because that's the same on both sides. So what do we have for little g, acceleration due to gravity? It's our good old constant there, 6.67 times 10 to the minus 11th, okay, Newton meter squared per kilogram squared. I have not allowed enough room here. Times, we already got rid of m1. The m of Earth is, there it is right there, so I'm just going to wipe that out of the way. Times that, divided by the distance squared. Well, there's the distance squared. So this is divided by 6.4 times 10 to the 6th meters squared. Okay, so that's how we're going to proceed here. Okay, now there's time for the calculator. Okay, so I'm going to go back to my calculator mode, press on the calculator, turn it sideways to get it in scientific notation, and we're going to start with the 6.67 times 10 to the minus 11th. So how do we do that? 6.67, don't do times 10, never do times 10, do your EE or EXP, and then do the, on my calculator I have to do 11 next, and then change the sign to make it a minus 11. Okay, now that's going to be multiplied by the mass of the Earth. Well, the mass of the Earth is 6 EE to the 24th, so I don't need a minus sign, 24th. Okay, divided by, whoa, that made me a huge number there, but now we're going to divide by, and this is where you need to have your parentheses, and we'll be doing this in lab 2, so get used to it. Open your parentheses and then type in your 6.4 EE 6 close parentheses squared and hit equal. And guess what you get? 9.8. When you round it to 2 digits, 9.8 meters per second squared. Oh, we didn't get the units. Let's see what the units are. Where in the world is my pen? There it is. Okay, so the G, the numerical value, is 9.8, and let's see what the units are. Okay, here we have meter squared. That will cancel that meter squared out. Here we have 1 kilogram here and a kilogram up here, so you have a per kilogram. Well, let's write what a Newton is. A Newton is a kilogram meter per per second squared, right? That's what a kilogram is. So this one remaining kilogram cancels this one out, and what are the units we have? Meters per second squared. That's a great unit for an acceleration due to gravity. That's where you get your 9.8. That's what they talked about before. They're doing it here, example 219. Now, here's another what if. Okay? What would be the value of G if the Earth was less dense with the same mass but double the radius? Okay? So here's what we're going to have then. We're going to have the same mass, 6.0 times 10 to the 24th kilogram, but we're going to double the radius, whereas before it was 6.4 times 10 to the 6th meters. Now the new radius is going to be 12.8. Double that times 10 to the 6th meters. So let's do the same thing here, except now we're going to double this and make it 12.8 times 10 to the 6th meter squared. Okay, so the only thing we do here, we keep the numbers we had just the same, 6.67, 6.67, EE, I have to do 11 change sign, okay, times same mass, 6, EE 24, that gave you a huge number, divided by, now this one you have to open your parentheses. Open the parentheses, and now we're going to type in 12.8 EE 6, close your parentheses, square it, and hit equal sign. What does your new acceleration due to gravity? If you doubled the radius, you divide the acceleration by 4 times. Inverse square, because you see that was a d squared. So that would give you 2.44, we'll just call it 2.4 meters per second squared. Same units come out of it, okay? And what if you took the 9.8 and divided it by 4? You get 2.45. We got 2.44. That's just round off error. Exactly. Any questions on that? Those kind of calculations is exactly what we're going to be doing in lab today. Okay? Now, I think we'll go on and close my calculator. I may plug it in just so we're going to have enough juice to do all the calculations we're going to do later today. So I'm going to plug it back in. Probably would make it, but I don't want to risk it. All right, let's go back to the PowerPoint. Any questions so far? Okay, we'll resume to the slideshow. We've done forces in circular motion. We've done Newton's law of gravitation. We calculated how they got the 9.8 meters per second squared. Very good. We talked about circular motion in space, the moon going around the earth going around the sun, Jupiter around the sun, any of the planets around the sun. Actually, the sun and the solar system going around the center of the Milky Way. It all works the same. Okay, so now let's talk about Earth satellites. This is on right-hand column of page 52. Now, the moon is the natural Earth satellite, the main one we've got. We've sent up there tons of artificial satellites. Now they have to, in order to stay in orbit, they have to travel more than 320 kilometers above the Earth. Okay? Now if you remember, the Earth's radius in that last problem was 64,000 kilometers. So you really don't have to be that much further, but you have to be quite a bit further, 320 kilometers above the Earth. They must also travel at least 8 kilometers per second in order to maintain orbit. If they're not going that fast, Earth's going to suck them down and crash into the planet. So they must be traveling. If you think about 8 kilometers a second, that would be about close to 5 miles per second. So that's moving really, really fast. Now, the example they give here is GPS. Now, here's what you're talking about with GPS. These satellites are what they call geosynchronous satellites. In other words, they stay the same place above the Earth all the time. As the Earth spins, they go right with it. So they are not moving relative to Earth. You got one here, one here, one here. I think I've read somewhere they have something on the order of 8 to 10 of these geosynchronous satellites around the Earth. They have to have plenty of them to get good coverage. Why do they need so many? Because you cannot determine where you are with GPS unless you have at least 3 signals. Okay? So let's say you're right here. That's in the middle of the Atlantic Ocean, it looks like. Okay? You're far from anywhere. You're trying to figure out where you are. If you get a signal from this satellite and you test it and run the math on it and stuff, you know you have to be a certain distance from that satellite. That would put you somewhere on this circle. Well, you hope you're not in Greenland because you're not on ground. You hope you're not in Upper Canada. You hope you're not in the mid-Atlantic states. You're somewhere out here, but you're somewhere on that circle. Here's another GPS satellite over here. This one, you have to be on this circle. Okay? Well, that narrows it down. You're either here or you're there because you're on both circles. But you don't know which. Are you really cold? This is right, puts you right on top of Iceland. Hopefully you're not there. So where are you though? Well, let's go from the third satellite here, and that puts you either here, here, or here. But because they all three have to line up, that's where you are right there. That's how GPS works. You have to have signals from at least 3 geosynchronous satellites. If you don't, you do not know where you are. Now, you may have more than 3. That helps you pinpoint and know exactly where you are. But you have to have at least 3. Okay. That's Earth's artificial satellites. Now, let's talk about another concept that relates to this. And by the way, I think maybe I should point this one out to you. This has to do with what they're calling weightlessness here. And if you've got your books, this is on page 52. Sort of a table over here, a figure over here. If you're at the center of the Earth, which we talked about before, and you're 1 radius away, that gives you acceleration due to gravity of 9.8 meters per second squared. If you double that, double your distance, you're 1/4 the acceleration due to gravity. Double again, you're 1/16. So it keeps falling off big time. Okay? And that table shows that. Your distance above the surface of the Earth, and it shows how your acceleration due to gravity falls off. Your mass does not change. Your weight changes big time. Weight and mass is different. Okay? Now, even when you're 20,000 miles above the surface of the Earth, okay, you still have some weight. If you weighed 154 pounds on the surface, you're down to 4.7 pounds now. Okay? Now, that's a great weight loss program. Just go into outer space and you lose weight. You don't lose any mass, but you lose weight. But when you come back to Earth, you're now got all your weight back. Okay? So astronauts appear to be weightless, but they're still affected by the acceleration due to gravity. Therefore, they cannot be absolutely weightless, but compared to what they're used to being, they feel weightless. They're actually in constant free fall going around the Earth, just like the moon is in constant free fall going around the Earth. Okay? if they're not tethered to that, I think this is the space station, if they weren't tethered there and they pushed off, there's not going back. You can't do it. So therefore they have to stay tethered to that so they can pull themselves back, because they're weightless. They don't have anything, not weightless, but close to being weightless, to pull them back. Okay, now there is a blurb at the top of page 53 which is on gravity problems. That's a pretty good little blurb to read. Okay, I think it would be very, very instructive to you. It's talking about this concept of weightlessness, or close to weightlessness, but it does have some pretty bad problems with it. Because guess what? We count on gravity giving us balance in our inner ear and places like that. If you're out there in space for very long and you don't have that, you can really become disoriented. It's also how we keep our muscles active, because we're always working against gravity. If you're out there near weightless condition, you're not exercising any muscles whatsoever, or very, very little. So you start losing muscle mass. You start losing strength. You start losing all sorts of things that you really need. So those are some of the gravity problems. Well worth a read there. Okay? Now, let's proceed. Oh, and that's the last slide in the slideshow. Okay? The weightlessness was the last slide we saw. That was on page 54. Now, people behind the science, guess who we're talking about this chapter? Good old Sir Isaac Newton. Okay? Now, this cannot be your source. If you choose to write on Newton, this cannot be your source. This can be a great place for ideas for your source, but you got to get the source out of the book, not in the book. Okay? And if you read through this, you'll see there's lots of other people mentioned here too. Or I think, at least I thought there was, yeah. There's the astronomer Edmund Halley, friend of Newton. So you could write on him. He's mentioned here. They mention Archimedes, Albert Einstein. Several people are mentioned there, so you can get several ideas for paper topics here. You don't have to write on Newton, but you can get several others. Okay, there is a little concept supplied on apparent weightlessness. If you want to look at that, you certainly can. Now, when we come to the end of a chapter, I'll say the same thing every time. Nothing replaces reading the chapter. Preferably you've read it before we talked about it in class, but if you haven't, go back and read it now, okay? Because you'll pick up and tie together way more things if you read the chapter than just listening to me talk, watching the PowerPoints and that kind of stuff. But once you've read the chapter, there is a summary at the end, and this is a pretty reasonably sized summary. Pretty good sized summary there. Almost an entire column on the left-hand side of the page. Okay? Now, after that, you have a summary of equations. Whereas in chapter 1, we had one equation. You could write it in about 3 or 4 different forms. But here we have 12 equations. Bottom of that column, and then the entire second column there. Okay, lots of equations, lots of ways to use those equations. Okay, then we have key terms. Now this one, even though it's a pretty good sized summary, it has a fairly short list of key terms. They list the page number in which they first defined or described, but they list the page numbers so you can find those pretty easily. They list them alphabetically, but put the page numbers. Applying the concept, a great thing to study for the test. And they have 47 of these. That's about a normal length. Okay, they're all multiple choice. Most of your questions on the second test will be multiple choice. The first test was mostly calculations. All the rest of your tests pretty much are going to be multiple choice. The final exam will be matching, not multiple choice. That's even easier. Okay, now you'll always have a few calculations, maybe 1 or 2. Okay, you may have a few fill in the blanks, but most of your questions on your test will be multiple choice. So a great thing to use to study is these applying the concepts. 47 multiple choice questions. Your test is only going to be in the neighborhood of 20 questions, so maybe a few fewer than that, but that's what you have. The answers are given on page 59, so you don't have to guess. You can find out. Now, if you work them and think of an answer, write it down, then you find out it's wrong, see if you can figure out why it's wrong. If you can, then you got it mastered. If you can't, ask in class, okay? We'll go over that. Questions for thought, there's only 12 of those here. Most chapters have around 16 or so it's a little on the short side. For further analysis, this is on page 60. There's 6, usually there's around 4 or 5, so one more, a couple more than normal. Then there's the parallel exercises. These are very similar to the problems we did on the examples. So these are worth your while to try to work some of those. The sad news is, well, I guess I'll give good news first. If you have a big book like this, then the answers for Group A parallel exercises are in the back. Group B is not back there. However, if you got that little book from the bookstore on the Bessemer campus, I don't know if they had any on the Birmingham campus, that little one, that one I don't think, I asked them to put the parallel exercises answers in the back. I don't have one of those books, but I've never been able to find the student who was able to find those. So I think they forgot to put them in. Shame on them. But there's 31 of those questions, well worth your effort looking at those. All right, any questions on Chapter 2? I have already posted, I think I showed it to you early, the test for Chapter 2. You already have the test for Chapter 1. A few of you have turned those in already. Now you have Chapter 2 test out there as well. I could not put it under Week 3 Test 2. There is a tab there that says Week 3 Test 2, but I couldn't put the test there because they did not put the plus sign for me to attach the test there. But you can send back your test there if you choose. You don't have to. You can attach it to an email or attach it to a message. Where I put the test was under Blackboard Messages, that little thing that looked like an envelope, upper right corner of your content page, that icon that looks like an envelope. It says Messages when you put your cursor on it. Click on that and you will see Test 1 and Test 2 are there. Okay. Any questions on Chapter 2? All right, how are we doing on time? 5:31, we only have about 15 minutes before we start lab. So let me go to Chapter 3. I think that's it. Nope. Where in the world do they put Chapter 3? Nope, not there. So I'm going to have to go out and find Chapter 3 again. I don't know why it messes up like this, but it does. So let me escape here, discard my annotations, and go back and find Chapter 3. There's Chapter 3. All right, now I'll go back to Zoom and see if I can find Chapter 3 now. There we have it. Okay. All this you have to go through. So, can you see my Chapter 3? Probably what you can't see is this taskbar that blocks most of my view, or a lot of my view. So I'm going to move it out of the way, and we'll be ready to go. We'll go from current slide. All right. Chapter 2 was motion. Chapter 3, energy. Now here's some differences. Remember when we started early today talking about momentum, we talked about motion. Okay, we started with displacement, a vector quantity, distance, a scalar quantity. Velocity, a vector quantity, speed, a scalar quantity. Acceleration, a vector quantity, the magnitude of acceleration, a scalar quantity. Force, a vector quantity, the magnitude of force, a scalar quantity. Momentum, a vector quantity, the magnitude of momentum, a scalar quantity. Okay, that's how we describe motion mostly, in terms of vectors, though you can talk about the scalar quantities. However, Chapter 3 is talking about energy. Now, energy is related to forces. It's related to lots of things. The difference is energy is a scalar quantity, not a vector quantity. All it has is a magnitude, no direction associated with it. So what's the core concept here? Energy is transformed through working or heating, and the total amount of energy remains the same. So guess what? Momentum was a conserved quantity. That was a vector quantity. Energy is a conserved quantity. The problem with energy is changes form all the time. Work is a form of energy. Heat's a form of energy. Displacement's a form of energy. There's just all sorts of forms of energy. So many, it's hard to keep up with who's on first. Now what they're showing here is a hydroelectric dam. On the back side of that dam, the water is probably up to about that level. Okay, you just can't see it, but it's up to that level. On this side of the dam, the water level is way down here. Okay, that difference in water level here, as the water falls through the sluices on the dam, they direct it so it hits propeller blades that turn giant turbines. Those turbines, we'll talk about in chapter 8, produce electricity. Chapter 6. Produce electricity. And here are some of the towers that are transforming that electricity, sending them out to various places. What we have here is the potential energy of the water on the other side of the dam becoming kinetic energy of the water inside the dam, changing to electrical potential energy in the power lines, and then going out and may be used for heating. Who cares what? Driving your cars, whatever. So energy is just changing all the time. Okay, changes form, changes the work, changes heating, changes all sorts of things. That's what makes energy sort of tough to deal with. It can flip and flop and change on you in an instant, but it's always conserved. You just have to keep up with what form it is. All right, so your fundamental law here is the conservation of energy. Okay, now what is energy? As we've already said, it can take many manifestations. Work is energy. Motion is energy. Position is energy. Radiation, light, is energy. Radiation in terms of things like nuclear radiation, that's energy, really high power energy. Heat is energy, a form of energy. You have chemical energy. You have nuclear energy. Mass itself is a form of energy. Hey, so many forms, so many manifestations. It's so easy to see how it gets so confusing to keep up with it because it flips from one to the other, to the other, to the other, but the total energy is always conserved. Now, what do we use as our main energy sources today? We have gotten hooked on petroleum. Okay? We power most of our cars with petroleum. We power our big trucks with petroleum, our ships, our aircraft. We use all sorts of fossil fuels for our energy sources. We have used in the past coal to a great extent, mostly making electrical energy. However, coal is very, very dirty. So they're moving away from coal. No matter what the politicians say, you're moving away from coal. Can't have it. I mean, it just isn't as efficient. As we saw behind the dam, moving water is a form of energy. Unfortunately, back when they built all these dams, just think in Alabama, we have Lewis Smith Dam, we have, oh goodness, what are the one near Gadsden, I can't think of the name of it is, but you have Lake Logan Martin, you have Lake Martin, you have Lay Lake, you have all these dams. Back when they first built them, okay, they produced large quantities of our electricity. However, we've used up most of the moving water that we can use. Most of the rest of it, if you tried to build a dam now, it would flood huge areas of the state because you need to have a lot of fall in the dam, like you saw back here. Look at the fall here, okay? If that was flat land here, you built a dam on it, it would cover everything, Okay, so we've used up most of the nice sites for moving water, and our energy piggedness, okay, we use so much energy, the percentage that we get from moving water is dropping. Still manufacturing a lot, but we're using so much more petroleum, coal, natural gas, and other things. Nuclear energy, for a while we were really going big time on nuclear energy. And then an event called 3 Mile Island happened at about the same time in Soviet Union. Chernobyl happened. Since then, Fukushima happened, and people have really gotten a lot more skittish about nuclear energy because there are some really dangerous, frightening things that can come with nuclear energy. It's a great clean source of energy, except when there's a problem, and then it's not clean at all. The waste material, not clean at all. Nowadays, we're doing a lot more with solar energy, but still a very, very small fraction of our energy use. We also are doing things with wind energy. Those turbines we saw at the very beginning, that's using wind energy to produce electricity. A great renewable energy source, okay? But they didn't even mention it here. Now, how do we use the energy? Well, certainly transportation. I mentioned cars, trucks, boats, planes. All those require some type of energy source, mostly your fossil fuels. Generation of electricity, okay? Some of your cars are hybrid cars, some of them are electric cars. You know, they're coming up with more and more, but guess what? Generating electricity goes back to fossil fuels, mostly. Some moving water, some nuclear, but most of it is still fossil fuel. So even though we're generating electricity, we're still getting that energy sometimes, quite often, from your fossil fuels. We also use energy to heat our buildings, to cool our buildings, to light our buildings, to do everything that we do, okay? We are using energy like ravenous pigs, okay? We are just energy hogs here, okay? A lot of the rest of the world is catching up too, but we've been leading the world in energy consumption, okay? But energy is always conserved. That's our fundamental law, okay? Now, let's look at some of these forms of energy. One of these forms, the one they mentioned first, and this is 3.1, is work. Work is a product, that means multiplied, of an applied force. So I said it was related to force. Here this guy is picking up a box, so he's exerting a force upward. Okay, so there's your displacement, there's your force upward, and the product of that applied force and the parallel distance through which that force acts. Since he's picking it up, the displacement of that is up, his force is up, the product of those two things is work. Now little w was weight, capital W is work. Little w was a vector quantity because it was a force. Capital W is a scalar quantity, that's work. Force, which is a vector quantity, times displacement, which is a vector quantity, but it's a very special kind of multiplication of two vectors. It's called the dot product. Okay, we're not going to get into that, but that produces a scalar number. Okay, so in the U.S. customary units, we use our force in pounds, our displacement in feet. That gives us foot-pounds. That's the unit for work in the U.S. customary system. Foot-pounds. Feet times pounds. Force times displacement. Well, actually displacement times force. Foot times pounds. In the U.S. and the metric system, or the SI system, your force is in newtons and your displacement is in meters, so you have a Newton meter. Well, you could call it a Newton meter, force times the displacement, but another name for that is a joule. Joule is named after a guy named James Prescott Joule, so the abbreviation is a capital J, just like the Newton is a capital M, named after Sir Isaac Newton. The joule, the abbreviation, is a capital J. That's your unit of work or energy, because they're the same in the SI system. In the U.S. customary system, foot-pounds. Okay. Now, we've already talked about the units of work and that's also for energy. Now, here's sort of a dumb story, but it's absolutely true. When we moved into the house where I'm sitting right now, this was many years ago, probably 25, 30 years ago. My wife loved the house, okay? But a previous owner of the house had built an addition in the back. Now, our house sits on a hill. A lot of things in Birmingham have hills. And the hill sloped from the backyard down to the sidewalk in the front. So it was sloping downward. They built the house on sort of a flat part way back in 1930. They did that. But when some previous owner wanted to add a screen porch and a den type area on the back of the house, they dug into the hillside, which made the house look squatty because the backside was the hill. They dug into that, and the windows in the back were very narrow windows because they were just above the soil level. Okay, and it also made the house look squatty, okay, in the back. Well, the other thing about it is now the hillside came down and all the water flowed toward that back wall. So I told my wife if we wound up getting this house, and she loved the house, I said we're going to have to do something to get the water to go away from the house so you don't have all that hydraulic pressure against the house. Also, we need to lower the soil level there so you don't have wood to ground contact, because you had the screen porch there, the wood was actually below ground level. Now, I'm sure that was okay for a few years because they used treated lumber, but guess what? Termites are going to get into that at some point. So my wife said, oh, well, good. I wanted a patio anyway. Not what I had in mind. I would plan just to do a berm there and get the water to deflect away from the house, and so nope, she wanted a patio. So that summer after we moved here, and that, by the way, was the first summer I worked at Bessemer State Technical College, and I only taught 2 classes for 5 weeks. We were on the quarter system then, and then I had the next 5 weeks free. So that time I spent digging out our patio, okay, with a pick, a shovel, and a wheelbarrow, pretty much. We did also get my wife's parents. They loaned us their rototiller, and she worked some with that. But that's what we dealt with. The reason I couldn't hire a bobcat or something like that, number one, we were sort of poor, but number two, there wasn't room for a bobcat to get in there and work because we had trees all over the place. We didn't want it hitting the house. So I started digging out the patio with a shovel, pick, and a wheelbarrow. Okay. The rest of the story we'll talk about later. Well, as I dug, at some point, I hit some rock. And when I say rock, I don't mean little stones. I hit a boulder. It was completely underneath the ground. I didn't know it was there, but it was right smack in the middle of where we wanted our patio to be. And I started digging around that rock, and it just kept getting bigger and bigger. I dug and I dug and I dug. I tried to move the rock. I tried to use a cheater bar and tilt the rock. I tried everything I could do, but guess what? I could not budge that rock. Now, I was doing this in the summertime, so I was sweating, I was grunting, I was groaning, all that kind of stuff. Was I working? You better have said if you were there, yes, you're working really hard. But in reality, in the physics term for work, I was not doing any work at all. If I could not move the rock, if there was a zero displacement, there is zero work. Here's a definition: force times the displacement. If this was a really heavy box, like maybe 500 pounds, I bend down and try to lift it up. If I can't get it off the floor, no matter how much force I put behind it, if there's no displacement, there's no work. So when I was digging that patio, when I hit that rock and dug and dug and pried and pushed and grunted and everything else, when I could not move the rock, I was doing no work. Zero displacement, zero work. Don't tell me I wasn't working. It was hot. It was terrible. Displacement has to be perpendicular to the applied force. Okay? If I had been able to pry it and get it to go this way, but I was pushing that way, I would still be doing no work, because the force has to be in the direction, parallel distance through which the force acts. So if you're lifting up and you just scoot it along the floor like that, technically you're doing no work. Okay? The force and the displacement has to be at least a component in the same direction. I was not making any progress at all. I was doing no work. Okay? Now, we've just gone over, so we will pick up next time. Why don't we pick up at example 3.1, top of page 65. Okay? That sounds like a reasonable place to stop. And what we'll do from this point on is, do y'all need to take a quick break or not? Let me know. You can get up and move around as much as you want to. I'm sort of stuck here, but I'm okay. Do y'all need a break? Anybody? Okay. Well, let me see if I can pull up. Say that again. Okay, that sounds like a capital idea. So why don't we take a quick break? I'm going to pause the recording here, and I'll do a little bit of work to try to get set up for the lab. So y'all go take your sandwich or whatever, take a bite, just get up and move around. We'll come back. Recording started again, and let's pick up. And I don't know if any of you have printed the lab yet or not. I'm going to scoot some things out of the way here, like this taskbar. I'll probably have to scoot some of y'all out of the way too, but we'll wait on that for a minute. And what I'm going to do is, I'm back in Blackboard, and where we are here is week 3, instructional materials. Okay, there were the 2 PowerPoint shows. We mostly were in chapter 2 today. We just got started in chapter 3. There's it says to go back to week 1 to get the link to your YouTube video playlist. The research paper instructions and locator car also given in week 1. The links are given there. Here is the lab for today. Now this is the same place we've gone, I think, for every lab so far. Probably the same one we're going to be going for largely. Okay, so if you are here, you can click on that link. It takes you right there. The last time I didn't make it as a web link. I just copied the file name, so you had to move this to the taskbar up here. Now you can just click on that. Here is the lab we're going to be using today. Physical Science 112 Lab 4.doc. Okay, and then on Thursday we'll be doing Lab 5, I think, if we get far enough along. We didn't make great progress in chapter 3 today, but if we get enough progress, we will do that on Thursday. All right, and then the library link is given in week 1 too. So what I'm going to do, since I don't have to do this, I've already got it open here. Here is, if y'all want to open it, you can. That's where you go to do it. I'm going to go to, I've already got it open. I opened it before class today. So I'm going to click on that. Okay. Now, can y'all still see this? Okay. Here is the offline access. Okay. What we're doing is simulations, physics. Okay. So I'm going to click on that. And what we're doing here today, I'm going to move you all out of the way because you can't see everything now. what we're going to be doing, the lab today is going to be, I believe it's called gravity. Okay, this is the one we'll be doing on Thursday, but we're not there yet. One of those, I think it's this one we're going to be doing on Thursday. Okay. Okay. Gravity and orbits. Okay, gravity force lab. This is the one right here. Gravity force lab, the basics. So if you want to click on that, you can. I'll go on and click on it now. Okay. And to get it open, go to the circle with the triangle in it and click on that. And it may take a little while to open. There it is. Okay. Now, I'm going to turn off the force values. And I'm going to bring this down. Now remember I said the masses have to be huge. And sure enough they are. 1 billion kilograms, 4 billion kilograms. Okay. I don't know how high they go, but we're going to go for a ways. Okay. Now the other thing I'm going to open is the lab itself. And here it is. Lab 4. You can get it at your week 3 instructional materials. That's where you get it. Okay. Now I'm going to move this to the top. Now I didn't fill in all the data, but I've just shown you how to do everything. I left off some of the things here. You go to the Blackboard page for this course. You go to, here I didn't put it in. You go to course content, and then you scroll down to week 3, click on instructional materials, and then this is what we just did. That's how we got there. Okay. Click on the simulations, then on physics, scroll down to gravity force lab basics, that's where we went, and click on the triangle and the circle, and that's where we are now. So the first thing I said was set the mass 1 and mass 2 to 1 billion kilograms. And it says record the distance between them. So let's go back to our, now I got to move y'all again. This is awkward, but doable. Okay. So what we're going to do is go back to there it is. Okay. There it is. So what's the distance between them? Y'all see it? 4 kilometers. Okay. Now, I don't think I can write on the screen, but we did something like this in class. Remember, in the SI units, okay, we deal with mass in kilograms. This is 1 billion kilograms. That's 1 billion kilograms. We deal with distances in meters. This is 4 kilometers. So this will be 4 times 10 to the third. Remember, kilo means 1,000. 4 times 10 to the third. So you can write down on your lab 4 kilometers if you want to. That's the distance between them. Okay, the mass is 1 billion kilograms. I've already said that. You don't have to write that down. And this is 1 billion kilograms here too. Now, let's go back to the lab. And it says calculate the force on mass 1 by mass 2. Now, I'm just going to try to see if I can write on this screen. I know I can't on the other one, but let me see if I can write on this one. Do you remember what the formula was for the force due to gravity? Let me see if I can write. No, I can't. Okay. So what I'm going to do is go to my whiteboard. Lots of different boards here, so let's go to the whiteboard. And we'll clear off the drawings here, and I'm going to do is move my taskbar up here out of the way. I think everything else is in good shape. So what's your formula? The formula here is force due to gravity. Do y'all still like red? Is G m1 m2 over distance squared. Remember what the G was? 6.67 times 10 to the minus 11. Units were Newton, meter squared per kilogram squared, times your mass 1, and that was 1 billion kilograms. 1 billion, 1,000 is 10 to the third, a million is 10 to the sixth, a billion is 10 to the ninth. So this would be 1 EE or EXP, whichever your calculator has, 10 to the ninth. Okay, that would be how many kilograms. That's your mass 1. The second mass was also that much, so that's your 1 EE. Now, actually, I should be writing that as 1 times 10 to the ninth kilograms. That's what a billion kilograms is. But I'm writing it this way because that's how you're going to enter it on your calculator. Okay, divided by, ooh, that's ugly, divided by 4 times 10 to the third, because it's 4 kilometers. Okay, so 4 times 10 to the third meters squared, because it's d squared. So this is your first mass, this is your G, this is your first mass, there's your second mass, and here's the displacement squared. All right. Now, I hope you have your calculators or phones, and let's see what we get there. Okay. My phone may run out of charge here because we got lots of calculations to do, but let's see what we can do. Okay, I'm going to turn my phone sideways so I can get the scientific mode. Okay, so again, y'all know how to do this. 6.67 EE, this times 10, that's your EE, and the EE key on my calculator is right over here. If you have EXP on your calculator, use that one. EE, and then I have to do the number first, 11, and then I have to change sign and make it a negative 11. Okay? Then I'm going to multiply that by 1 EE 9 and multiply that by 1 EE 9. That's 1 billion kilograms. And I left off my unit here. Where is my pen? I forgot my other kilograms here. This is also kilograms. Okay. And then I'm going to divide that by this 4.4 times 10 to the third meters squared. Okay. Again, you do scientific notation. 4 EE 3. Oh wait, I messed that up. I messed it up. I need to change that. I may have messed it up big time now. When I divided, I needed to open parentheses first and then done 4 EE 3 close parentheses squared equal. Error, I got an error. Sorry, I didn't do my parentheses right. So I'm going to start over again. Okay, 6.67, so it happens in the best of families. Okay, EE 11, and my fingers are big and fat and the keys are really small, so I have to watch everything I type. Only one of the ones showed up there. Change signs to minus, times 1 EE 9 times 1 EE 9 divided by, this time don't forget the parentheses, open parentheses, 4 EE 3 close parentheses squared, the squaring key, and then press equal. What do you get as your force because of 2 1 billion kilogram masses 4 kilometers apart. Okay, what do you get there? Did anyone punch it on your calculator? That was this one right here. That would be, calculate the force of mass 1 on mass 1 by mass 2. Okay, this is what it looked like here. What was the force on this mass by that mass? Okay, anyone get it, what it was on your calculator? Okay, now you must have messed up an exponential there, because it shouldn't have an e to the minus 9. So let's go back and redo that. Okay, so let's go back to the whiteboard. Okay, now let's start again. 6.67 EE 11 change sign. Now if your calculator doesn't do a change sign like that, do that that minus sign in parentheses in front of the 11. That works also. My phone, I have to do the 11 and then change sign. So that's your first thing. That's this part right here. Times 1 EE 9, that's this one, times 1 EE 9, that's this one. And then we divide it by, now this one you have to open the parentheses here to get this to work. Open parentheses, my parentheses is over here on the left here, upper row, open parentheses, 4 EE 3, because it's kilometers, close your parentheses and square it. Okay, and then press your equal sign. It may be you didn't square it. I don't know if you did or not, but that's what I got. I think we got the same numbers, but you had a different exponent. It's just 4.1. And here, folks, we're not really dealing too much with scientific with significant digits. I would just call that 4.2. 4.2 newtons. Okay, and now why newtons? Okay, let me find my pen here, because here is kilogram squared here. That cancels that kilogram and that kilogram. So those cancel out. Here is meter squared here in the numerator, a meter squared here in the denominator. That cancels out, and that leaves you with Newton. So I got 4.2, I'm going to call it, newtons. Did anyone else get anything close to that? Yay or nay? Anybody? Okay. All right. We're going to do just like we see here. We're going to start with the G here, 6.67. So I got to get my calculator turned sideways. Okay. 6.67. Now, instead of doing times 10 to the minus 11, I do EE, and then for my phone, I have to push the 11 first, then change sign and make that minus 11, okay? And then that's the first term here. I'm going to multiply that by your times key, and here we have 1 EE 9. That's this one right here. 1 times 10 to the 9th, 1 EE 9. Then multiply that by the second one, another 1 EE 9, 1 EE 9. And then divide that by, here's your division line here, but we need to open that parentheses, open parentheses, 4 EE, 4 times 10 to the third, 4 EE3, close the parentheses and hit the squaring key. The squaring key is this one right here on my phone. Hit that and then press my equal sign. And that's where I get 4.166 blah blah blah. I just rounded 4.2. Now you could put more digits if you want to, but we really don't have justification for those. I think 4.2 will be fine. Got it? Okay, has everybody done that one and got an answer close to this? Yay or nay?
Yes.
Good. All right. Now, let's go back to our, I don't know which to go to now. Let's go to this, and we're doing the force on mass 1 by mass 2. Okay? Now, these are showing these guys are holding these apart. If that's 4 billion kilograms, they got a lot of work to do. But in reality, it's only about 4.2 newtons of force. So really, it doesn't take that much. But they're 4 kilometers apart. That would be about 2.5 miles apart. So yeah, they're not going to feel a lot of force from there. Okay. Now the second question on here, or the third question I guess it is saying calculate the force on mass 2 by mass 1. Okay. Now, same picture.
I'm so sorry. You did start the recorder, right?
Yes, it did. Yeah, right there. You probably can't see it, but I did start it. Yeah. Okay. Okay. So now we're going to calculate the force on mass 2 by mass 1. Well, guess what, team? Say again? Yes, it will, because remember Newton's third law, that a force, if this is exerting a force on that one, this one's exerting an equal but opposite force on the other one. So we're not dealing with the signs here. If you wanted to, you could put 1 plus and 1 minus. We're just doing the magnitude of the force. And sure enough, that's what we got. Same answer. Okay? Now, is that same answer because they were the same masses? Not necessarily. Let's go back to our lab, and it says set mass 1 to 2 billion kilograms and then calculate the force of mass 1 on mass 2, on mass 1 by mass 2. So what we're going to do here is go back to the Gravity Force Lab Basic, increase this to 2 billion kilograms. Okay? Now, remember our formula has nothing to do with which one's which. We just enter the same thing, except let's go back to our whiteboard here. And what we'll do is change this one. Oh boy, it's not going to let me change. What a pain in the neck. Okay. For some reason, after a while, it doesn't let me erase. What's that? Okay, which color you want it to be? Black, lavender, pink. Say again? Okay, okay.
What you're trying to show us is what's going to change, because one of these are going to change from 1 times 10 to the 9th.
And the other one's going to be 2 times 10 to the 9th. Okay? Does that make sense the way I've drawn it there? This is a 2 now rather than a 1. If you punch them in, just like we did before, we Southerners punch things, we don't press. Okay, let's do that. 6.67 EE, I have to do 11 then change sign, times 2 EE9 times 1 EE9 divided by, open parentheses, don't forget to do that, 4 EE3, close parentheses, square it, and then press equal. What is your new one?
Okay, so that's going to be 8.3. So number 4 was 4 kilometers as well?
It's 4.2 newtons. 4.2 newtons, same units. The next one, whatever that is going to be that 8.3. If I can find, oh, I'm on the wrong pad. I've got two pads here, and here we go. That would be 8.3 newtons when you change that one. Okay?
So number 5 is 8.3 newtons.
Let me see which number. I don't have it in front of me now. Let me go back to this, and that's this one. Okay. Set mass 1 to 2 billion kilograms. Calculate the force of mass 1. That was your 8.3, number 4. Now calculate the force of mass 2 by mass 1. Guess what? It doesn't matter which one's bigger and which one's smaller. The forces have to be equal and opposite. So if this one was 8.3, this one's 8.3, right? Newton's third law, action, reaction. It doesn't matter which one's bigger, which one's smaller. The force is the product that we just did. Make sense? Yay or nay? Okay. Now, we're going to set the mass 2 to 2 billion kilograms. So let's go back to our, and let's bump this up to 2 billion kilograms. Okay? And guess what? Do the same type calculations. Now, do y'all want to continue doing these together as a group, or do you feel confident enough?
Yes, sir.
Okay, so let's go back to our calculation board, the whiteboard. Okay, and this time we will increase this one to a 2. Okay, so we'll do our calculations just like before, turning your calculator sideways, or computer, phone, whatever you want to call it. Okay, 6.67, you're going to know that number after a while, aren't you? EE 11 minus, I have to do it that way. If you have a different calculator, do it your way, times 2 EE9 times another 2 EE9 divided by, remember to open your parentheses, 4 EE3, close that parentheses, square it, and then hit your equal sign. What are you up to now? Anyone do it?
15.6.
Yeah, that's what I got. I'm going to round that to probably just 17. 17 newtons. Okay? So you doubled the mass, you almost double the force. Double the mass again, just one of the masses, and you basically double it again. Okay? Now, everybody got that? Okay. So let me know when you want me to stop, and you can just play with it, because I know I'm probably slowing you down. Let's see what it says next. Now it says that was number 6, right? Now calculate the mass on the force of mass 2 by mass 1 when they're both 2 billion kilograms. Guess what that is? Same answer. Okay, so whatever you had for 6, you have the same for 7. Newton's third law. Okay? Now we're going to set mass 1 to 3 billion kilograms. So let's go back to our thing and set this to 3 billion kilograms, leaving mass 2 at 2 billion. Okay? So what we're going to do now is go back to our whiteboard. Whenever you want to stop, I can stop and you can continue. Okay? Let's pick a different color now. We've used red and lavender. We still have black, pink, brown, yellow, orange, a different shade of brown, light green, dark green, middle green, light blue, dark blue, and middle blue. Which one you want? Which blue? Dark blue. Okay, there we go. Okay, this is going to be a little bit like this. So now we've increased this one to, let me just see if it'll let me erase now. No, it won't. Okay, so this is going to go to 3 kilograms, 3 billion kilograms. Okay, so we'll go back to our calculator, and this gets to be pretty much old hat, doesn't it? Okay, clear the screen, and we've got 6.67 EE 11 negate, okay, times, this time it's 3 EE 9 times 2 EE 9 divided by, open that parentheses, 4 EE 3, close parentheses, square it, and press the equal sign. What are we up to now? The blue, the dark blue, is going to be about, anyone do it? Anybody?
34.
Now I got 25. Did I do it wrong? No, you're not doubling. You increased it by 50%. So I think that comes out 25, approximately 25. Okay, go back and check your math. Maybe I did it wrong. 6.67 EE 11 minus times 3 EE 9 times 2 EE 9 divided by, open parentheses, 4 EE 3, close parentheses, squared, equal. Yep, I got 25 again. So you weren't doubling, you went from 2 to 3, which is multiplied by 1.5. Okay, so if you had 17 before and multiply that by 1.5, you're going to be close to 25. Yeah, round off error, but you're close to it. Everybody got it? Any question? Yeah, got it? Okay, so let's go back to our thing. That was number, this one, 8, wasn't it? What was number 9? What's the force of mass on mass 2 by mass 1 then? Exactly the same, that 25 again, right? Because Newton's third law, whatever one exerts on the other exerts on the one. They're in opposite directions, but they're still do. Okay, so now let's set mass 2 to 3 billion kilograms. So let's go back to our Gravity Force Lab basics, And now we'll bump this one up to 3 billion kilograms. Wow. Okay. Now let's go to our whiteboard. Okay. And I'll bump this one up to 3 billion. 3 EE9. Okay. So go back to our calculator. 6.67 EE11 negate. Now if you have a scientific calculator, you probably will do a minus 11. Okay, whatever. Times 3 EE9 times another 3 EE9. Divide that by, open parentheses, 4 EE3, close parentheses, squared, equal. What are you up to now? Anyone do it? Take your time. Let me know when you get an answer. Anybody? Yeah, that's what I got. About, I'm just going to round it to 38 just because I don't want to write so many digits. But 37.5 is about what I got to. Newtons. Okay, that's with 3 and 3. Okay, so that goes here. When you get 3 and 3, that was this one, number 10, right? And guess what the force on mass 2 by mass 1 is? Yep, same thing, 38. Okay, so let's move down to set mass 1 to 4 billion. Okay, let me see if anyone's coming in. Let me make sure I haven't left somebody hanging. Okay, no. Okay, 14, set mass, or 12, I'm sorry, set mass 1 to 4 billion kilograms. So let's go back to the gravity force lab and set mass 1 to 4 billion kilograms. Okay, now do your calculation. I'll clear the screen. 6.67 EE11 negate, okay, or negative 11, whichever yours do, times, this time it's 4 EE9 times 3 EE9 divided by, open parentheses, 4, oh, I'm on the wrong page. No wonder I can't see what I'm doing. Okay, let's go back to whiteboard here. 4 EE, did I open parentheses? I hope I did. EE, whoops, that didn't work right. 4 EE3, close parentheses, squared, equal. All right, what are you up to now? Okay, we have just changed. Okay, we need a new color here. We've used lavender. We haven't used black. We've used red. We haven't used pink. We haven't used, I don't know what color that is. It's sort of a a dark red kinda, then we haven't used yellow or orange or brown. We haven't used any of the greens, light green, middle green, or dark green, and we used a dark blue but not a light blue or a middle blue. So what you want to use? Anybody? Can I say again? Green. You want light green, middle green, or dark green? You want what? Money green. Okay. Let's do that as the middle green. Okay. Now we're going to increase to 4. Okay. And I think I punched everything in on the calculator. And what will that 4 become? That would be, did anyone get it? 50. Right on the nose, 50 Newton. Not exactly, but pretty close, 50.025. Okay, good deal. Now, that's number, I can't remember what it is now. That was number 12. Guess what 13 is? Let's calculate the force of mass 2 by mass 1. It doesn't matter. It doesn't matter. The forces are equal and opposite. So that's also your 50, right? Newton's third law. Got it? So now let's do 14. Which, I'm rounding them, yeah.
So 50, you put it to 50, instead of 50.1, you put it to 50.
Yeah, I just put 50. I got 50.025, which to me rounded to 50. Okay.
Alright.
Okay. But you can put as many digits as you want to. I'm writing on the screen. Frankly, the fewer digits I have to write, the better. Okay.
Alright.
Good deal. So number 14, we're going to set mass 2 to 4 billion. So let's go back to the Gravity Lab Basics and bump this up to 4 billion kilograms. Okay. So that's going to take us back to the whiteboard. And we will do the second mass to 4 billion. Okay, so let's see what we've got there. 6.67 EE11 minus times 4 EE9 times 4 EE9 divided by, open parentheses, 4 EE3 close parentheses squared equal. And what do you get now? Error? Oh no! I get approximately, I didn't put approximately before, but I could have, 67. Now let's go back and do it again and make sure I did it right. I didn't make an error. 6.67 EE11 minus times 4 EE9 times 4 EE9 divided by, open parentheses, okay, 4 EE3 close parentheses square equal. Yep, I got it again. Approximately 67 newtons. Okay. So even though we're increasing by billions of kilograms each time, we've only gone up from 4.2 Newton to 67 newtons. That's distance squared, 4 kilometers apart. That really knocks off the gravitational response pretty quickly. Okay. You want to keep going or what? Okay, the next one is, we've set mass, that was 14, set mass 2 to 4 billion, mass 1 was 4 billion, calculate the force of mass 1 by mass 2, but then when you calculate the force on mass 2 by mass 1, same thing. What was that? About 67 newtons. Got it? 16. Set mass 1 to 5 billion kilograms. So let's go back to the gravitational force. Let's set this to 5 billion kilograms. Okay? And take that to our whiteboard. Okay. Now, I wish I could erase. Can't erase. If this gets too crowded, we can change it. What color you want to go to now? We haven't used black. We haven't used pink. We haven't used sort of a reddish brown. We haven't used yellow, orange, or dull brown. We haven't used light green or dark green, and we haven't used light blue or middle blue. What you want? Anybody, I don't care. Black, why not? It shows up really well. Okay, so now we're increasing this to 5. So let me set down my calculator so I can type in or push in a 5 here. This will be a 5 here. Okay, so let's go to our calculator and punch these in. 6.67 EE 11 minus, okay, times, and this time it's 5 EE 9 times 4 EE 9 divided by, open parentheses, 4 EE 3 close parentheses squared equal. What you up to now? I wish I could find my pen. There it is. Perfect. Okay, I'm just going to, because I don't like to write digits any more than I have to, I'll just put approximately 83 newtons. Perfect. Very good. Y'all seem like you're catching it really, really well. Do you want to continue, or do you want to work on your own? Because I may be slowing you down. Whatever you want. Okay. All right. Then we'll go to new screen. We'll go back to our lab. We just increased mass 1 to 5 billion kilograms, leaving mass 2 at 4. But now we're going to, we calculated the force of on mass 1 by mass 2, but now we do mass 2 by mass 1, and what would that be? Exactly the same, whatever that was, 83 approximately. Okay? So now we're going back to mass 2 and increase it to 5 billion kilograms. So let's go back to our thing here, bump it up to 5 billion kilograms, go back to our whiteboard. Yes. Okay. Now, okay. The exponential notation, I don't know if you can, yeah, EXP. On some calculators it's EXP. On mine it happens to be EE. It's usually one of the other. So if you have an EXP, that's the one you hit.
Okay,
Yeah.
and if you just have an EX, then you're just hitting the EX?
Okay, now I don't know what EX is. Oh, E to the X, like this one right up here.
Yes.
Okay, no, that's an exponential. That's not a power of. That's not a scientific notation. Scientific notation is either EE or EXP. This is E to the power. That's a completely different function.
I don't have that on my phone.
You don't have either EE or EXP? Okay. Do you have a caret key that looks something like this? Looks like a housetop. No. Do you have something that looks like this? Let me see. What are some others? I can't think of any. It's either EE, that's what's on mine, and it could be capital EXP or P, that's not an R, P, or little EXP. That means exponential. Okay, what kind of, are you using a phone or a calculator?
I have a
Phone.
phone.
Is it iPhone or a Samsung?
Android. It's a Samsung.
Samsung. Okay, I don't have a Samsung, so I don't know how it looks. Okay.
Trust me, I'll figure it out.
Okay.
I mean, I know my equations, so I'm putting my equations together.
Right.
I would eventually figure it out. It just might take me a little time.
Okay. And see, a lot of today's lab is getting used to doing scientific notation, dealing with big numbers, doing calculations like this. So that's basically the purpose of the lab. So because we're doing the same thing over and over again. Okay. So now we go to increase set mass 2 to 5 billion kilograms. So we're on number 18 now, right? Okay, so let's go to 18 and we'll go to the whiteboard. Oh, did I change it on the thing here? Yeah, I changed it there. So now we'll go to the whiteboard and we'll change the mass 2 to 5 billion. Billion is 10 to the 9th, so it's EE9. Okay, so 6.67. Does anyone else have a Samsung that your calculator has a key like EE or EXP? I wish I had one, but I don't. Mine's an iPhone. If you have a scientific calculator, that maybe worked a little better. I had one and I think it either died or someone borrowed it and never returned it or something. So 6.67 EE 11 negative, okay, times 5 EE9 times 5 EE9 divided by, open parentheses, 4 EE3, close parentheses, square, equal. Anyone got an answer there? That's what I got, 104 newtons. Have you also got an iPhone, or you got a calculator, or what are you using? iPhone, okay. So yours probably looks just like mine. I just don't know Samsung, so I don't know what to do with that. Okay, now that is number, oh my goodness, I'm getting tired. Okay, That was number 18. How about 19? Same masses, same distance, same everything, equal and opposite. So if you wanted to be putting some of these plus and some minus, that would be fine, but you don't need to. We're just doing the magnitude of the force, same thing, 104, right? Okay, now we're going down to set mass 1 to 6 billion kilograms. Okay, go to the new share, go to the gravity force lab. Let's bump this up to 6 billion kilograms. Okay, so let's now go to our whiteboard and do that one. Now we have to come up with a new color again, and we're not going to use white. We've already used lavender and black. We've used red. We haven't used pink. Sort of a reddish brown, yellow, orange, dull brown, light green, dark green, medium blue, or light blue. What you want to do? Anybody? Say again? Surprise you? Is that what you said? Okay, well, I'll just do the next one I see here, and that would be pink. Okay, is that surprise enough? Okay, I think we just increased the 5 to 6. So this is going to be 6 EE. Now that's getting awfully hard to read. Let me see if I can. Okay, you know what I think I'll do? I think I'll erase the whole slide and start over. Okay, it's going to take me just a little while, but not too bad. If I could get this to erase, I was hitting on the wrong pad. Okay, so what we have now is the force due to gravity is equal to, I'll leave off the formula because we know what it is, 6.67. I'll go on and put times 10 to the minus 11 Newton meter squared per kilogram squared, if I could write. And for some reason this thing just erased most of what I put down. Meter squared per kilogram squared times, now what are we up to now? 6? Was that it?
Yes.
6 times 10 to the 9th kilograms times, the first one is 5, right? The second one is 5 times 10 to the 9th kilograms, and dividing all that by 4 times 10 to the 3rd meters squared. All right, so on my handy dandy calculator, I'll do the 6.67, nope, didn't register, 6.67, didn't register again, my fingers are too fat, 6.67 EE 11 negate times 6 EE 9 times 5 EE 9 divided by, open parentheses, 4 EE 3 close parentheses squared equal. What you up to now? I can't remember where you left off before, but I'm up to 125. Is that what you had? Or did we already have 125?
No, we had 104 was the last one.
Okay. Does 125 sound right? I may have punched it in wrong, so let me know.
Yes, I got 125.
Okay, good.
Okay, did you guys get 125.0625?
Yes. I just didn't write all those digits down.
I told y'all we figured it out.
What's that?
I told y'all we figured it out.
You think you got it figured out? Excellent. Way to go. Okay. Now what we're going to do next is go to that was this one, number 20. 21 would be exactly the same. 22 is set mass 2 to 6 billion kilograms. So let's go to here and bump that up to 6 billion kilograms. 6 billion kilograms. Okay? Look how the forces are getting bigger and bigger and bigger. Okay? Now, but you see they're equal but just opposite in directions. Okay? So, let's go to a whiteboard. Now, let's go to a new color. You want me to surprise you again? Okay. I want to go with this dark reddish brown. Okay. Now, didn't we already go to 6 here? I don't know why it's not showing up. I've gotten lost where we are. Let me go back. We're 6.6 or 6 or 7.6? 6.6. Okay, so this will be going up to 6. Okay, so pulling out our handy dandy calculator, 6.67 EE 11 negate times 6 EE9 times 6 EE9 divided by, open parentheses, 4 EE3 close parentheses squared equal. What you up to now? Anyone up to 150? I may have punched mine in wrong, so let me know if I got it wrong or right.
I have 150.
Okay, 0.075, but that's close enough for government work. Okay, so that was number that was 22. Okay, what will 23 be? Same, 150. Okay, 24, we're going to set mass 1 to 7 billion kilograms. Okay, so let me see if I can remember where we are here. Go there and bump this up to 7 billion kilograms. Okay, I don't know what you mean by check mark. You mean when you're squaring the number? Okay, you see on my calculator, if I can find my finger, there it is. Okay, you see x squared there. There's x cubed. Wait, there's x squared, there's x cubed, there's x to the y. So this is the one that says x squared. That's your squaring key. Okay, good deal. These cameras are pretty amazing. Okay. All right, so now let's go to our whiteboard. And we're going to bump this 6 up to a 7. Okay? And we'll punch that one in. If I can get my calculator to do. 6.67 EE 11 negate, okay, times 7 EE 9 times 6 EE 9 divided by, open parentheses, 4 EE3 close parentheses square, okay, and then press equal. What you up to now?
175.0875.
That's about what I got. Yep, exactly. Now this is pretty interesting. We seem to be going up by 25 newtons every time now. Okay, that is interesting, really interesting. Okay, so that was 6.7 or 7.6. So let's go and see where we are now. Okay, that's 7, and the other one is still 6. That was your 175 newtons. This one would be exactly the same, 175 newtons, just in the opposite direction. Okay. Now we're going to set mass 2 up to 7 billion kilograms. Okay. Now, by the way, folks, we have gotten our 25 questions, so that's really all we have to have, but it wouldn't hurt to go on and do a few more. Do y'all want to do it on your own, or you want me to continue doing it with you? The total page here goes up to 43. Okay, so not, well, I was just saying you've done 25, so you got your 25, you know, but if you had made an error, 25 counts a whole point off. If you made just one error with 43, that's just a fraction of a point off. Okay, so, but I think everybody's been doing them together. It just depends. Do y'all want to work on your own, or you want to keep doing? I'm going to grade it based on 43, but you know, so you want to keep going? What's that? You want to keep going or work on your own?
I say let's keep going.
Okay, so we did 7 and 6. Was that our last one? So let's now move to, if I can find, oh, no, I should be on the right screen here. There we are. Let's go to 7.7. That's a pretty tall character, isn't he? 7.7. So we'll go to our whiteboard and do 7.7. So we did that 7. Let's get this one. So I guess we need a new color now. Want to go yellow? So this will now be 7 here. Orange, okay, we'll do orange. Sounds like an Auburn fan, okay. Oh, I see. So this will be 7 too. 7 here, and I'm going to go on and go back to black here, so because that's what we were before, but I've gotten behind a, okay, so we'll be 7 and 7 here. So let's pull out our calculator and go. Okay, I've still got plenty of charge, I think. So 6.67 EE 11 minus times 7 EE9 times 7EE9 divided by, open parentheses, 4EE3 close parentheses square equal. What you up to now? This time we went a little more than 25. 204, approximately 204. I thought we were in orange, but we didn't quite get orange, so we'll go back to orange next time. Okay, I guess I changed to put that 7 in there and didn't get it right. Okay, but it's okay, it's still a different color. Okay, that answered, come on, where is my, here it goes. That answered, goodness, I'm tired of sitting. Yeah, 26 and 27 were both 204. Okay, 28, we're going to set mass 1 to 8 billion kilograms. Okay, so let's go back here and set it up to 8 billion kilograms. Ooh, bigger. Okay, and let's go to our whiteboard then and go it to 8. Goodness, my nose itches, we must be going to have excuse me. Thank you. Okay, let's go back. Goodness, I'm losing my headset. Back on again. Find my microphone. There it is. Okay, let's go back to orange. Aren't you glad we did that? Okay, and we'll go this one to 8. Okay, I've got too many moving parts here. Okay, so, whoa, why is it doing that? I haven't even touched the screen yet. Okay, I can't get it to erase. Okay, we'll just do an 8 here. Okay, 8 and 7. Okay, so let's go to the white. Well, I'm on the whiteboard. Let's just do it here. 6.67 EE11 minus times 8 EE9 times 7 EE9 divided by, open parentheses, 4 EE3 close parentheses squared equal. What are we up to now?
234.
Okay, I punched something in way wrong. Let me go back and I did something wrong because I'm way off. 6.67 EE11 negate times 8 EE9 times 7 EE9 divided by, open parentheses, 4 EE3 close parentheses square equal. What did you say again?
233.45.
Okay, so I'm going to round that to 233 newtons. But yeah, you can put the 0.5, no sweat. Okay, now the next one. Okay, let's go back and see where we were. Okay, that was 8 and 7, was it? So that was 28. 29, same thing, 233 or 233.45, whatever. Now we're going to move mass 2 to 8 billion kilograms. Okay, so mass 2 bumps up to 8 billion. Okay, and go to the whiteboard here. Okay, let's try it here. And even though I've got one, I'm still going to do another orange here. 8 billion, so both of those are 8s. Okay. Then with the calculator, 6.67 EE 11 negate times 8 EE9 times 8 EE9 divided by, open parentheses, 4 EE3 close parentheses square equal. What you get?
266.8.
Yeah, I'm going to round that to 267. Pretty interesting, huh? Okay. So that's our okay. That was 8 and 8, so that was 30. 31's the same, right? 267 approximately. Okay, 32. Let's bump the first one up to 9, leave the second one on 8. Okay, so let's go to, I bump this up to 9 and go to our whiteboard. All right, so it looks like time for a new color. Okay, we still haven't used yellow, brown, light green, dark green, light blue, and middle blue. Surprise again. Let's do yellow. So we're going to move this one to 9. Now that's getting hard to read, so I'm going to do it here. 9. That will be an 8. Well, I wish I could, but you see my eraser thing, you can't see it, it will not come on. Okay, so I could clear the screen and start over. You want to do that? Let's do that. Okay, now remind me where we are. Yeah, let me, okay. The force due to gravity is equal to your G, which is 6.67, times 10 to the minus 11. That's Newton meter squared per kilogram squared times, and was it 9? 9 times 10 to the 9th kilograms times, and we were starting this one with 8, right? 8 times 10 to the 9th kilograms, and divide all that by 4 times 10 to the 3rd meters squared. Okay. Now, 6.67 EE 11 negate times 9 EE9 times 8 EE9 divided by, open parentheses, 4 EE3 close parentheses square equal. What you up to now?
300.15.
That sounds good to me. About 300 newtons. Okay, because remember the units cancel out. The meter squared cancel out with that meter squared. Kilogram squared cancel out that one, and you're left with newtons. Okay. Now, that was number 9 and 8. That was this one, 32. 33, same thing. 300 newtons. 34, bump up mass 2 to 9 billion kilograms. So let's go to our thing and bump mass 2 up to 9 billion kilograms. So look how long these forces are getting here, but they're still always equal and opposite. Okay, Newton's third law. Okay, so let's go to our whiteboard, and this time we're going to increase this 8 to a 9. Okay, oh my goodness gracious. 6.67 EE 11 negate times 9 EE 9 times 9 EE 9 divided by, open parentheses, 4 EE 3 close parentheses squared equal what you're up to now.
337.66.
Okay, I'm going to round that to about 338. But 337.668, perfectly fine. Okay, 338. I just don't want to write any more digits than I have to. Okay. All right. Y'all okay with keep going? Okay, let's go back and see where we are. That was 9 and 9. So if I can get my screen to show up again. That's 34 and 35. Yeah, 9 and 9. So we're ready for 36. We're going to see if we can go to 10 billion. Now, I haven't gone this high before, but let's see if we can. Let's go to 10 billion here. It looks like we still can. Yep, we could. And we'll go to the whiteboard with 10 billion. And in this case, let's change colors again. We were yellow. We've already done orange. You want to do that brown this time. Since we're on new screen, we could go back and repeat some colors. So let's make this right here 10. Okay, so handy dandy calculator, 6.67 EE 11 negate times 10. Now you don't have to change scientific notation, it's still 10 EE 9. You could have done 1 EE 10, same thing, okay, times 9 EE 9 divided by, open parentheses, 4 EE 3 close parentheses squared equal. What are we up to now?
375.
Yep, 375. About 375 newtons. Very good. So that would be our number 36 and 37. Very good. Okay. We're getting near the end now, folks. Okay, they're in sight. Okay, so now we're going to set mass 2 to 10 billion kilograms. So let's do that. Go here and set to mass 2 to 10 billion kilograms. There we go. Boy, the forces are getting longer, aren't they? Okay. And go to our whiteboard, and this will now be this one will go to 10 times 10 to the 9th, or you could have done 1 times 10 to the 10th. It doesn't matter. Okay, so let's get our calculation. 6.67 EE 11 negate times 10 EE 9 times 10 EE 9 divided by, open parentheses, I don't think something came out right there. The numbers aren't nearly big enough, so I'm going to stop and go back. Okay, something doesn't look right. 6.67 EE11 negate times 10 EE9 times 10 EE9 divided by, yeah, that looks like a better number there, open parentheses, 4 EE3 close parentheses squared equal. What you up to now?
417.
Looks good to me. 417 newtons. That's with 10 and 10. So that is our number 38 and 39, 10 and 10. All right, 40. Okay, last group here. Okay, so let's go to set mass 1 to 11 billion. Okay, so we bump that up to 11 billions. Oops, it won't go to 11 billion, folks. We are through. Okay, so forget about your rest of them. That's as high as it goes. Okay, so that worked out pretty well. Okay, now I don't know why it wouldn't go any higher, but it wouldn't, so let's end it there. So let's go back to our screen share and just on here leave those last 4 blank. Okay, we only went through 39, right?
Yes, sir.
Sounds good. I was tired of punching numbers anyway. So we got up to 39. You'll be scored based on 39. Good deal. Was this useful or was it too repetitive? Okay. All right. Well, y'all were champs for hanging in there that long. Way to go. Any last thoughts, questions, parting shots before we go? I'm going to stop my sharing unless y'all need to see something else. Do you? Okay, I'm going to stop sharing. And then unless there's any other questions, we'll end the meeting for everybody. Any last thoughts, parting shots? Good deal, folks. We will see you on Thursday. Okay? We'll continue with chapter. Yes. What's that?
Okay, so at first, like with me, like with the lab, I have to go. I know you said we have to basically like my Microsoft. I told you I had a problem with it. So I've been going to a relative house and printing them off.
Mm-hmm.
Like I still have lab 1. Like, is it okay if I still turn those in?
Anytime you can get it in, that would be great. The sooner the better, but yeah. I know that people have all sorts of things. I remember when we first went off campus, my computer died twice. My internet went out once for more than 2 days. I know what it's like to have all sorts of electronic difficulties. So the main thing, get it done. Sooner the better, but yeah, no sweat. Just get it done. All right, glad to. All right, y'all take care. We'll see. Oops, I didn't mean to end the meeting, but I did. Okay.